Finally woke up, drank 2 cups of coffee, and now I'm gonna be. Now I'm gonna be starting my study session, which is quite tragic because it's already 3:30 p.m. Leonard streamed for 2 hours, I streamed for 4 hours last night, which is quite tragic because I streamed for 5 hours total last night. But today we'll redeem ourselves by studying for 10 hours straight. 10 hours. So, task number 1. I prepared some questions for myself. So I'm gonna do the questions right now. What are the energetic conditions for a complex to form? Why can transition metals form multiple oxidation states? Because the 3D and 4S subshells are in similar energy levels. How come ions with ionization energy can form complexes? 干嘛？行吧，
就给你炒个菜，把中午那个给那什么了，行不？
行吧，
炒个鸡蛋虾仁儿，
嗯，行吧。
炒个鸡蛋虾仁儿，然后整一点大米饭，然后再弄这个，行不？鸡蛋虾仁儿全是那菜就没有了，好吧？或者再炒一个绿菜，啊
行，
，OK。你几点吃来？6点到7点上课啊？
嗯。
OK。
Oh, let's take a look at our final finished work. Okay, I don't think you can see it. Oh, what? You can see it here, but you can't see it here. I don't want to correct these questions. I'll just pretend they're right. See if anyone is watching me. Let's go. Let's double our earnings. Why did it get dislikes? This is running every day for 100 days until I can run my first marathon. Today we're going to be taking a day off from running, but I'm not going to stop training, so I'm going to be keeping myself active by doing some boxing. Now, I started boxing around 4 years ago when I was 15 years old, now I'm 19. I started off by watching YouTube tutorials and doing home workouts such as shadow boxing and conditioning work, working on my fitness and technique as a beginner. Over time, I joined a boxing gym and started working on my footwork. Eventually, I started sparring and developed a fear of sparring due to the hard sparring sessions I've had. Not very smart, but it was partially my coach's fault for putting me into those sparring sessions. I relentlessly worked on my speed and power every week on the heavy bag and put boxing as one of the main focuses of my life. At some point throughout my journey, I stopped boxing for a while and focused more on running and lifting, and that's when my speed and power fell off by a lot. I recently joined an MMA gym to get back into boxing and learn how to kickbox at the same time, and at some point maybe even learn how to wrestle and do Brazilian Jiu-Jitsu. For now, I'm mainly working on technical sparring to sharpen my instincts, and at the same time, I've gained 10 kilos of weight so my speed has taken a hit. Throughout my martial arts journey, I'd like to sharpen up my reflexes and regain the speed I previously possessed and one day do an official match, whether that's boxing or kickboxing under an actual organization. Anyways, this was me training for boxing. Let me know if you would like to see more of this kind of content, and I'll see you guys next time. This is running every day for 100 days. It doesn't seem bad to me.
Has mess. which means the one has mass, the will has mass, which means the one has the mass that will be exerted by the gravitational field, right? So we are going to calculate the gravitational force. And in this chapter, we're going to, the second field is the electric field. Electric field. And electric field is going to act on the charged particle, which means if the one object has the charged particle, okay, so they will be exerted by the electric field, right? Understand that?
Yeah.
Exerted by the one object has the charged particle, okay, so they will be exerted by the electric field, right?
Exerted on by the electric field. The electric field is a field that exerts force on charged particles.
Right? Understand that?
Yeah.
Charged particle, okay. Charged particle. Okay, and the third one field, that is the we're going to learn in the next chapter, that is magnetic field.
Particle is CLE. God damn it, I wrote it wrong.
And the magnetic field is also acts on the charged particle. So if one object has the charged particle and has the charge, okay, and in this field, in this magnetic field, we are going to have the force. The force we are going to call it magnetic force. Okay?
Okay.
Understand that?
Yeah.
Hello? Okay. So in this chapter, we are going to learn the one of them. The one of them that is the electric field. So if the one object has the charge or the carrier charge, so they will have the electric force. The force. Okay. So the force we all the force we all going to call it the Coulomb force. Have you ever remembered the Coulomb force? What is the Coulomb force? The formula.
I forgot.
Oh, okay, you forget, right? Okay, the Coulomb force, the formula, that is the F equal the K, the charge quantity 1, and charge quantity 2, the product of the charge quantity, and the over the R square, which means if the left one we have the positive charge, and the right one we have the negative charge. Negative charge. Oh, and we can separate in some certain distance, like the R, we are going to use the r to represent the distance. Okay.
Yeah.
Understand that? So we have the force. We are going to know if the same charge, if the two charge have the same sign, which means the same positive or same negative. So we have the attraction force, the will attraction. Okay. So the force, we can use the formula to calculate the magnitude. The force equal the K, that is the electrical constant. We can to check it for the reference table in our past paper. Checklist. And the charge one is the left one, the charge quantity. The charge quantity. And the Q2, that is the right one, the negative of the charge quantity. And the R, that is the distance, right? So the denominator, that is the R square. Okay, so we are going to use this formula to calculate if we have two charge separating the two different position, and they are separating by some distance R, and we can use the Coulomb's force formula to calculate the magnitude of the electrical force. Okay. Right?
Yeah.
Okay, so this one is the 7.1. And so you might understand what is the main definition of the electric field. Electric field is just like the environment. If the one object going into this environment is only acts on charged particle, which means if the one object has the charge, okay, that will be exerted by the electric force. Then we are going to calculate the force, the how magnitude that is. We can use the Coulomb's force, this formula. This one, right?
Yeah.
Okay, so we're going. The first one is the definition. We have to memorize the electric field definition, because the axial will to in the past paper. This one, our highlighter. So the definition of electric field is defined as the region of the space in which where a charged particle experiences the force, right? So we always call it the force field. Okay. Right?
Yeah.
Understand this? Okay. And this one, we are going to calculate the how strong or how weak that is the electric field. This one, right?
Take a look at the notes. The charged particle could be stationary or moving and will experience electric force in the field. All charged particles create their own electric fields. These fields exert an electrostatic force on other charged particles. Like charges, positive and negative repel each other. This means that the force on each charge are away from the other charge Opposite charge, positive and negative, attract each other. This means the force on each charge is towards the other charge. The size of the force changes with the distance. Right.
Yeah, understand this. Okay. And this one. We are going to calculate the how strong or how weak that is the electric field. So electric field strength is which means is the how strong or how weak it is in this environment. And we can use the sign E to represent. And the formula that is the F over the Q. So F is we have previously calculated the electric field force, right? This one is the force, and the denominator that is Q. The Q represents the charge.
The electric field strength at the point is defined as the force per unit charge acting on the positive test charge at the point. Force per unit charge acting on a positive test charge at that point. Force per unit charge. So the equation is electric field strength force per unit charge. It's important to use the positive test charge in this definition as this determines the direction of the electric field. Recall the electric field strength is a vector quantity. It is always directed away from a positive charge and towards a negative charge. This direction is also denoted by the direction of the electric field. Field lines are drawn perpendicular to the charge. Field lines directed away from a positive charge. Field lines directed towards a negative charge. The force and the denominator, that is Q, and the denominator is Q. The Q represents the charge.
Okay, so we can use this formula to calculate the how strong or how weak of in this environment. The environment represents the electric field strength, right? Understand that?
Electric field strength.
Yeah. Okay. After we learned that, and we are going to draw electric field lines. Okay. Do you have remember what is the definition of the electric field lines? Mm-hmm. Electric field lines. Have you remember it? What is the electric field lines?
Denotes the
Direction
of the
and the
field.
force of the one field.
The electric field lines just like an instrument to help us to visually to imagine this in this environment, and the charge produce the electric field. And what is it? Like if if the left one, if the charge is the positive, okay, and the electric field we can join from the center of the charge, the positive charge goes to the infinity, like this.
Infinity.
Okay.
Electric field lines from the to
Understand
infinity,
that?
from infinity
Draw
to
like
the
how?
center.
Yeah.
Oh, okay then.
Okay, right. And after we learn that, and here's the example. Okay, look at the example. If the charged particle in the electric field, and we know that the electric field strength is the 3.5 and the 10 and and we want to
0.3.
calculate the charge of the particle. So which one formula we can use to calculate? Okay, it's easy, right?
Yeah.
Okay. After that, we are going to learn if we put two charges in some point, if we put the positive charge, the left one, the negative charge, the right one, and we can separating the distance like the radius, and we can use the formula. The formula we always call it the Coulomb's law. Okay.
Okay.
Coulomb's law.
And it's just like the another form. We can use another form that is saying the k q1 q2 over r square, and we can the k actually equal the 1 over 4 pi and times permittivity epsilon, right? The k actually equal
Permittivity. What is permittivity, man?
the 1 over 4 pi and times permittivity. This one we also
Coulomb's law. The force between two charges. Two pi permittivity r squared.
was called epsilon. right?
Epsilon.
So
I don't know what
the
that
true
is.
you don't know what is it, right?
Yeah.
And this is the explanation. Epsilon is the
Right.
permittivity of the free space.
Epsilon is permittivity of free space. What does that mean? Permittivity of free space. It's a constant. Okay, I guess I just have to know the constant.
So we can find it in the topic, or in the topic that will tell you what is and how is it, and what is the magnitude of the permittivity of the free space. Okay.
Okay.
Okay. And we can
Gonna go take a shit. Testing, testing, testing. Testing. Gonna go take a shit. Gonna go take a shit.
use this formula to calculate the electrostatic force. Electrostatic force, which means the two charges keep the at rest and not moving, right? And this one, and keep it static. And the separating distance is radius r, and we can know that this one is the positive, this one is the negative. Okay, negative. And the two charges had attraction force, right? Attraction force. Why? Attraction force. Why the two charges has the attraction force?
Because of the electric field interaction.
Okay, yes. Okay, so the electrostatic can be divided into two. Electrostatic Mhm.
You were lagging a bit.
My internet lagging, right?
Yeah.
Okay, I will turn it. Wait for a second. Particle, the negative charge particle into another positive charge particle. So this phenomenon will change, right? And the left one is positive, and the right one we changed into another positive. So the force, electric force, will change into the rebelling force, right? Not the attraction force. Okay, okay. So the definition of the Coulomb's force is the electrostatic force between the two point charges is proportional. It's proportional for what? It's proportional for their charge product. Okay? It's proportional to their product of the charge, right?
Yeah.
Is Q1 times Q2.
Okay.
And inversely proportional to the square of the separation. And like R square, right? Is inversely proportional, right?
Oh.
Okay,
Yeah.
so here's the 2 point. The first point is the proportional, the charge product. The second keyword is the inversely proportional, okay, to the square of their separation. So that's the definition of the Coulomb's force, right?
Yeah.
So we have to write the two key points, the first point and the second point. Okay. And we have to introduce the epsilon is one. Okay. This one is simple. It's the permittivity of the free space. Okay. The free space we can find in this topic or in the paper is the reference, and the topic will give you the value that you can use the value to calculate, to take into the formula to calculate. So you don't need to memorize it, right? Okay.
Yeah.
Okay. And so we can see this example. There's the alpha particle, and situated the 2 micrometer away from the gold nucleus in vacuum. And we assuming they are point charges. The top just one must calculate the magnitude of the force acting on each of the charges. And we know the condition. Atomic number of the helium is 2, and atomic number of the gold is the 78 or 79.
Yeah.
And the charge of the electron is 1.6 and the turn negative 19, right? So how to solve this question? Over R squared.
Meters.
Need
Yeah.
problem?
No
Understand
problem.
it? Okay, no problem. And this one. After we have learned the electric field or the definition.
Electric field strength describes how strong the electric field is at a point. A point charge produces a radial field. A point charge produces a radial field. A charged sphere also acts like a point charge. The electric field strength E at a distance r due to the point charge Q in free space is defined by this. Electric field strength E at a distance r to a point charge Q. So this is not the force, this is the field strength. Field strength originally was force over charge, now it's this. Which does make sense. Okay, I get it. I get it. Permittivity of free space, epsilon squared.
Or after we have learned the electric force, right? And we are going to use another terminology that is the due to the charge, a point charge. And we want to know the how magnitude of the radial field. And in this environment, the strength is what? Okay, if you get the point charge and we want to calculate the electric field strength, and using the electric field strength to describe how strong or how weak of the electric field, so we can use this formula. Okay, look at the formula. The denominator is the charge quantity, right? If the point charge is the point, okay, and we can draw the
She's more like a het to me. Come on, mate, come on. This many questions? Holy shit, I'll be spending the rest of the day doing it. Alright then, let's finish this and then go
electric
back to
field
there.
lines, like from the center to the infinity, right? Okay.
Yeah.
And the charge quantity is the denominator. Okay, the positive. And the denominator, we can use the 4 pi times permittivity, the product. And another is R square. The R square is, we have to memorize it. The R equal the distance from the center of the charge. Okay. The distance represents the distance. The R represents the distance from the center of the charge, right? From center.
Yeah.
Okay. If we put the point charge in this point, so the R is this one, right? If the point charge in this point, so the R is this one, right? Understand that?
Yeah.
Okay. So we can use this formula to know that the electric field strength in radial field is a constant or not constant. The question. Using this equation, and we know that the electric field strength is the constant or not constant.
Not constant.
Or you
varies
vary
with
the radius.
the
Varies with the radius.
distance.
Okay, so the result is not constant, right? Okay.
Yeah.
If the radius increase, so the denominator will increase also, right? And the whole fraction will decrease, right? So the electrical field strength will decrease, right? Okay. The radius increase, so the R square will increase also, and the E will decrease, right? Because R square is the denominator, right?
Yep.
Okay.
Yeah.
Okay. And this one, if we take the E decrease by the factor of 4, if we put to change the value, change the distance R is double, so we can get the E is the original value is the 1/4, right? Okay.
Yeah.
If R and change into or double R, and the E will change into original value 1/4, right?
Yeah.
Okay, this one. And after we know that, we can use this graph. We will go into plot graph. And the plot graph, the first, we need to, the R is the x-axis, and electric field strength is the y-axis. Okay, so we use the formula, the E equal the 1/4 pi permittivity, and 1/r squared. Okay, and we can regard this part as a constant, right? Regard as a constant. Okay, regard as a constant. And the denominator, R is squared, right? So the graph Y is curved. Why the graph is graph? Why the E versus radius graph is a curve, is a decreasing curve. Why? Use this formula to extend it.
Because when R increase, there's an inverse relationship.
Okay, yeah, because we regard this part as the constant, so we can use the math knowledge to regard as the linear function, right? Y equal m times x. Okay, and y value is the E, right? And the x is the radius, right? And the m is the slope, right? Slope is this one. Okay.
Yeah.
Okay, so the final.
Confusing.
No, the graph is the curve, the down curve, and the concave bar, right? And the decreasing like this. With the in this process, with the radius increase, so the E will decrease exponentially, right? Okay.
Yeah.
Okay, so this is the graph of the E versus radius. Okay, and we can see the vertical example. And if we want to calculate the strength of the electric field at a constant of 2 meters away from an electron, okay, that is the away from an electron, and we also need to state the direction. Okay.
Okay.
The point charge. So the topic tells us the point charge is electron, right? And we are going to state the direction. Okay. To solve it, what is the answer?
So 1.6 times 10 to negative 19 over the 2 squared times k.
Okay, so you use the formula, right?
Yeah.
This one formula. Okay, and right. And the direction.
Direction is away towards the electron.
We have previously not the negative positive. The negative positive. The direction is from the center to infinity, from infinity to the center, right?
Yeah.
Okay. From infinity to the center. Okay. Right. So we can write by this from infinity to the center of electron. Okay.
Yeah.
All right. And let's continue. After we have learned the Pauling charge and electric field strength, the formula, and Coulomb's force formula, and what's the definition of the electric field strength, and we want to construct an uniform E, the uniform strength, okay, the uniform electric field strength, which means in this environment, the any point in this environment, the any area in this environment, the E is always the same, right? In this environment, the E is same, right? In this environment,
Yeah.
if the any point the E is same in this environment, we can call it the environment. So we construct a uniform, the word uniform or uniformly electric field, right? Okay, understand that?
Yeah.
Okay, so how to construct the uniform electric field? You can see the graph. How to construct uniform electric field? First, we need two metal, right? Two metal. This
Yeah.
one is metal. This one is metal. The two parallel metal and the parallel metal, and we can connect the circuit. If the current from this direction and to this metal, the left metal, okay, and this metal, the left metal will be charged by the positive charge, right? The positive charge, right? So the positive charge, the left side, right, and the negative charge, the right side, okay. And from we have previous note the electric field.
Positive test charge has an electric potential energy due to its position in the electric field. The amount of electric potential energy depends on the magnitude of charge and the value of electric potential in the field.
The field lines, and the electric field lines is from the positive charge of cinder to infinity, right? So we can draw the parallel. So every single parallel lines in this process, right? Like this one, okay, right? From the left metal to the right metal, okay. Every single lines are parallel each other, right?
Yeah.
Okay, and the distance between the every single lines is equal. Okay, and we can set up the distance by the two parallel metal is d. The distance d. Okay, and in this two parallel metal in this environment, we have constructed the uniform electric field, right? Okay, so in this environment, the two parallel metal and E is everywhere same, right? Okay, the E is same. The direction is from left metal to the right metal. Okay, the direction of the electric field. Electric field is from left metal to the right metal. Okay, this is the arrow, right? Understand that?
Yeah, understand.
Okay, and this is the definition. This one.
Work is done on a positive test charge Q to move it from the negatively charged plate A to the positively charged plate B. This means its electric potential energy increases. Electrical potential is defined as the amount of work done per unit charge at that point. A stronger electric field means the electric potential changes more rapidly with distance as the test charge moves through it. Hence, the relationship between electric field strength and electric potential is summarized as the electric field strength is proportional to the gradient of electric potential. I don't know what that means. A stronger electric field means the electric potential changes more rapidly with the distance. If the electric potential changes very rapidly with distance, the electric field strength is large. If the electric potential changes gradually with distance, the electric field strength is small. I think I get it. Electric field can be defined in terms of variation of electric potential at different points in the field. The electric field at a particular point is equal to the gradient of a potential distance graph at the point. Okay. Let's finish this point.
This one. The electric field strength is proportional to the gradient of electric potential. And this word is the electric potential. You know what is the meaning of the electric potential? Electric potential is what? Is what? And we have not the electric field strength, have not electric force. And we want to know electric potential. What is the definition of the electric potential?
Is it the distance times the
Distance time,
force?
the force, the distance time force. But you can see this one. Okay, the electric field potential is like if we put a point charge from the left side metal to the right side metal, okay, and we have charged the potential energy, electric potential energy, okay, and we use the potential energy, the energy over the charge quantity, so one can get the value. The V is the potential, okay, right? So we can use the fraction to understand it.
I don't get it. I don't get it. I don't get it. I do not get it. Dude, I got 49 views. God damn it. I got 1 view. Alright.
The second lesson we'll talk about capacitance. So, what is the capacitance? Remember? What is the capacitance?
Store charging or discharging.
Okay, yeah. You just mentioned that they have the two process, right? The first process is to charge the energy, right? Charge the capacitor energy. And the second process is to discharge the energy. Show me what we have learned in the last lesson. Look at the contents from the 7.1 to the 7.8.
The electric field strength,
Yeah.
electric
What do you
field.
have? Don't need any of the current to pass from the left side to the right side. Okay, there's no any equal the capacitance times the potential difference between. The V is the potential. Okay, right? So we can use the fraction to understand it. The denominator is the electrical energy, which means from this one, this position to the right position, right? The electrical potential energy. Understand that the E is the electrical potential energy, and the denominator is the charge quantity. The charge quantity is represent the point charge. This one, okay? So the fraction is the value. The value we always call it electrical potential. Okay, so we can use the V to represent. Understand that?
Yeah.
Okay. So this one is the electrical field strength. Is proportional to the gradient of the electrical potential. Okay, and look at the graph. If you want to plot another graph, the another graph is the electrical potential versus the radius. Okay, versus the radius, and the E is the change. The E is the rate change of the potential over the change of the radius, right? The denominator is the change in potential, and the denominator is the change in radius. Okay, and we know that with the increase of the radius, and the potential will decrease, right? According to the formula.
Yeah.
Okay, and if we put the point charge from center to infinity in infinity position, the potential or the electric field strength is approximately equal to 0, right? Understand that?
Yeah.
Okay. And the below the graph is the positive graph, and this one is negative. So the denominator is the change in radius. Okay, and we know that with the increase of the radius, and the potential will decrease, right? According to the formula.
Yeah.
Okay, and if we put the point charge from center to infinity in infinity position, the potential or the electric field strength is approximately equal to 0, right? Understand that?
Yeah.
Okay, and the below the graph is the positive graph, and this one is negative. So different charge. The positive charge have the curve from the infinity, positive infinity. The curve decrease to 0, right? Approach to 0, right? And if the point charge is negative charge, and the graph will be from negative infinity, and will decrease to 0, right? Okay, understand the two different charges, the graph, potential versus radius graph. Understand that? Yeah. Okay. And okay, we have to know the key features of the graph. The first one, and I will highlight it. The value for V, the V's electrical potential, right, are all negative for negative charge, right? So if the charge is a negative, okay, so the electrical potential are all negative. If the charge is the positive, so the electrical potential is all positive, right? And the curve tendency as the radius increases and the voltage against R follows 1 over R relation, right? For positive charge and 1 over negative 1 over radius.
I'm not registering. The values for V are all negative for negative charge. The values for V are all positive for positive charge. As R increases, V against R follows a 1 over R relation for positive charge and negative 1 over R relation for negative charge. The gradient of the graph at any particular point is the value of E at that point. The gradient of the graph at any particular point is the value of E at that point. Electric field strength. The graph has a shallow increase or decrease as R increases. The electric potential changes according to the charge, creating the potential as the distance R increases from the center. If the charge is positive, the potential decreases with distance. Okay.
Right? Understand that? Yeah. Okay. And the gradient of the graph at any particular point is the value of E. And what is E? What is E?
Potential. Wait, no, the energy.
No, energy. Electric field strength.
Electric field strength.
The E is the electrical field strength. The field strength, right? Not energy. Okay. If you use another formula, we can get to the electrical energy. And electrical energy, we can write this energy equal the charge quantity and the times V. This one, the E, the letter E, is electrical energy, right? Not this, right? Not the gradient, right? Okay, understand that?
Yeah.
Okay, so if the electrical potential versus radius, the gradient is electrical field strength. Okay, not electrical energy. Okay, if we want to calculate electrical energy, so we can use this formula. The formula is the point charge quantity and times the potential, right? The electrical potential. Okay, right?
Yeah.
Okay, and this. If the electrical potential change according to the charge, creating the potential as distance r increases from the center. If the charge is positive, okay, and we can get the potential decrease with the difference, right? And if the charge is negative, the potential increases. Why? I don't want to know why.
Because the magnitude decrease and it's negative.
Okay, right? Because we negative mass, right?
Yeah.
Okay, negative mass become mass. Okay, and look at the example. Okay, an electric field is set up between two pairs of the oppositely charged plates. Okay, charge plate, like the metal plate. And we set x and set y. A graph showing how the electric potential V varies with the distance is shown for both set x and set y. And the question just want us to state and explain which set creates the largest electric field strength. Okay, so we can use the graph to explain it. How to solve this question? We have no the graph. The axis is the distance. The
Confusing the hell out of me. The electric field is set up between two pairs of oppositely charged plates, set x and set y. Graph showing how the electric potential V varies with the distance d is shown for both set x and set y. Why is V increasing with distance? then set y. Because when it's closest to set y, it has the largest potential difference. Electric potential.
Y-axis is the electric potential, okay? And we have a radian. The radiance is what? The gradient is what? The gradient is the electric field strength, right?
Yeah.
Okay, so the gradient, the E equal the change in potential, right? Electric potential over change in distance, right?
Yeah.
Okay, so how to state and explain which set, the X or Y, will create the largest electric field strength? Which one? Is the X or Y?
I think X.
Why? The reason?
Because
Why the
it
X?
has larger V.
In larger V?
Yeah.
Or maybe you can see the larger gradient.
But why? What? Why is it increasing?
Oh yeah.
Okay, but you can see the graph. Okay, the gradient, the X gradient, the X gradient is greater than the gradient of Y, right?
Oh.
Right? The gradient of X, set
Yeah.
X,
Yeah.
has the greater gradient, right? Than Y. Okay, and we know it. The gradient represents what? The gradient represents what?
The
Electrical field strength, right? Use this formula. Okay, and we, this one, the gradient of the graph at any particular point is the value of E. The E is electrical field strength, right? Okay, so the gradient is electrical field strength, right? Understand that?
Yeah.
And so the larger gradient means larger electrical field strength, right? Understand that?
Stronger electric field means the gradient. Changes more rapidly. So the gradient is higher. No, what? What? Stronger electric field means the electric potential changes more rapidly with distance. Electric potential changes more rapidly with distance. So the gradient is larger. V equals ED. E is constant. Oh. Electric potential changes more rapidly. So the electric field changes as well with distance. It's the potential difference at the point. If the electric potential changes very rapidly with the difference, electric field strength is large. This is very abstract.
Right? The gradient of x,
Yeah.
Zx,
Yeah.
has the greater gradient, right? Than y. Okay. And we know it. The gradient represents what? The gradient represents what?
The
Electrical field strength, right? Use this formula. Okay. And we, this one, the gradient of the graph at any particular point is the value of E. The E is electrical field strength, right? Okay. So the gradient is electrical field strength, right? Understand that?
Yeah.
And so the larger gradient means larger electrical field strength, right? Understand that?
Distance is
Right?
Yeah.
So that's the reason why the set X has the largest electric field compared with the set Y. Okay. So we can write like this: the set X largest, and the reason is the set X has larger gradient, right? Okay. Because the set X and the set Y are both linear, right? The linear we can distinguish from the slope. Okay, the slope to distinguish which one has the larger gradient, right? Okay, understand that? Okay, and this one. After we have learned electric field strength and the potential,
magnitude of electric field strength in a uniform field between two charged parallel plates is defined. Ugh, this is all too confusing to me. E equals V over D. Because with a single charge, E constantly decreases. But in a uniform field, E is uniform. Parallel plates. So, electric field strength is not defined by units. Am I ever gonna get this?
And when we want to calculate the uniform in the environment of the parallel plates, the uniform field strength, how strong or how weak it is. So if we have the parallel plates and in this environment we have a uniform field and we want to calculate the value, so we can use this formula. Okay, the formula next the graph. Two parallel plates, and this one is the positive, the left metal, positive, the right metal is the negative, right? And the field lines, electric field lines, we can draw like this. From left metal plate to the right metal plate. Okay, right? Understand that? And the E electric field strengths are same, right? In the environment, the parallel plates. Okay, and the V is what? Remember, the V is the potential difference between the plates. Okay, the V is represent the potential difference between the plates. It's like the volume here, the potential difference between the two plates, right? Okay, and the d is the distance between the two parallel plates. This is the d, the distance. Okay. Okay, so if we have now the potential difference between the connected to the two parallel plates and the distance between the two parallel plates, and we can use the two variable to calculate the uniform. Okay, as the uniformly electric field strength, right? So you might know what is the definition of uniform field strength. You know that? Understand that what is the definition of uniform field strength, right?
Not really.
So you might use this formula. Uniform field strength, like in this two parallel space, this space, the every point like this point, this point, this point, this point, the every point always equal, right? Always equal. If the two parallel plates, okay, in this space, the every point we have the uniform field strength. Okay, so we can call the two parallel plates produce a uniform field. Okay, if we want to calculate the magnitude of the electric field strength, so we can use the formula. The formula, the denominator is the potential, and the denominator is the distance between the two parallel, right? Two parallel. The formula, the denominator is the potential, and the denominator is the calculate the magnitude of the electric field strength. So we can use the formula. The formula, the denominator is the potential, and the denominator is the distance between the two parallel, right? Two parallel distance. Okay, right? Understand the formula?
Yeah, understand now.
Okay, and like this, the simple circuit. Okay, so this is the positive, so the current will pass through this line, and this is the positive, right? And if we want to draw the uniform field lines, so we can from the positive plate to the negative plate, right? And draw the parallel, okay, the parallel field lines, right? And the E is same in every point in this space, right?
Yeah.
Okay.
Field
And we
strength
can
is
look
the
at the
same
table.
at every
If
point.
two parallel metal plates are separated by the 3.5 centimeter and have a
Potential
difference of the 7.9 K voltage, potential voltage. And this example just want us to calculate the electric force acting on the stationary charge.
Calculate the electric force acting on a stationary charged particle between the plate that has a charge of 2 points. How do you do that? Electric force. So first we calculate the electric field strength. Electric field strength. Then what's the relationship between force, charge, and electric field strength? Okay, electrostatic force, the Coulomb's force over charge equals electric field strength. So we calculate electric field strength by doing potential difference, electric potential over distance. Calculated
dipole
it.
between the plates that has the charge is the 2.6 and times 10 negative 15, right? So how to calculate the value? How to calculate the value? Use which formula?
Calculate the
Electrical force. We want to calculate the force, but we have no the parallel metal plates and the parallel separating some distance. The distance is the 3.5 centimeter, and the potential difference is the 7.9 k volt, right? So we can use the two variable to calculate what is the E, right? Because E equal the V over D, right? Right?
yeah, calculate E first.
Okay. And second, use another formula. Another formula is what? We want to calculate the force, electrical force.
I forgot.
Okay, the force equal the E times charge quantity, right? Okay, this is the electrical force. In the beginning, we have not this one. Let's go to 4. Okay, this one, right? Electric field force, right? This one, F, right? Okay, so F equal the product of the E times Q, right? And we use the first formula to copy the E, right? And we need to find the charge quantity, right? So we can get the answer is the force, right? Okay, understand it right now?
Yeah.
Okay, so come back, and we have found the E, and we need to find the charge quantity. The Q is what?
2.6 times 10 to negative 15.
Okay, so we can use the formula. The force equal the E. The E we can substitute. Use
E
the
over D.
D over D and times Q, right? The Q is the 2.6 and then times 10 and negative 5, right? And negative 15, right? Okay, and to take every variable into the equation. And the voltage is the 7.9 and times 10 and 3, right? And distance is the 3.5, but times 10 and negative 2, right? And times 2.6 and times 10 and negative 15, right? So we can get the answer, the result, right? Use this formula, okay? Understand it? Okay, right. So in today's lesson, we have learned, okay, look at content. We have learned what is the definition of electric field and electric field strength, right? And electric force between the two charges. And the 7.4 chapter is the electric field due to the point charge and electric field and the potential, right? Okay, and we have learned the electric field between the parallel plates, okay? And the 7.7 is the electric potential, okay? So this is the what we have learned in this lesson, right? Okay, so today's lesson is over, and I was
The fuck? What the fuck?
Tell me what we have learned in the last lesson. Look at the contents from the 7.1 to the 7.8.
The electric field strength.
Yeah.
Electric field.
What is the definition of electric field strength?
Electric field strength is the gradient of voltage and gradient of electric potential over distance from the charge. The charge, yes. Okay. It's the force per unit charge acting on the positive test charge at that point. For force per unit charge.
The
how density or how weak, right, in the field and exerted on the charge carrier, right?
Yeah.
It's like the how dense, the keyword that is how dense, that is how strong or how weak the field, right? So that is the main idea of the electric field strength. Okay.
God. did 3 questions.
And how about 7.3? Electric force.
It's the product of the two charges over the radius, the distance squared.
Mhm.
And
So
then,
the force we always call it Coulomb square, right?
Yeah.
And the formulas is right there, right? The force that is the proportional to the product of the two charge, right?
Yeah.
And inversely proportional to the what?
the distance squared.
Yeah. Okay, no problem. And how about the next section? 7.4. Electric field due to a point charge, which means the point charge will produce electric field. And how's the formula? It's like.
Forgot.
And let's quickly review it. And due to the point charge, we can use the formula, the force over charge, okay? And the result, we can use the E, right? The E is the field strength due to the point charge, right? And use this formula. Substitute the force into and the K, product 1, product 2 over R squared, okay? And over the Q1, right? So the final result, that is the Q, O2, right? Charge 2 over R squared, right? So the final result, that is the formula of electric field due to the point charge. Understand that?
Yeah.
Okay. And 7.4, guess what? Potential. What is the definition of potential?
Electric field due to a point charge is the electric field strength. Oh my god. Oh my god, this is so weird. I got a lot of work to do. I'm gonna study all night. Study until I finally collapse. Wait, 2 chat messages? Okay, I gotta join the meeting. Okay.
Hello, can you hear me?
Yeah, hello.
Okay. So you have understand the question you asked me? The potential.
Not really, because
Okay.
why do they both have a for a set x and set y? Why do they both have a graph? Because they are oppositely charged. If they're oppositely charged, why do they have the same type of graph?
Pardon?
Because you said that the the graph is from the negative charge.
Yeah.
But these two are differently charged, then why do they have the same graph?
Okay.
Shouldn't one of them be opposite?
Okay, and the D, you refer to the D, okay? You refer to the D, the work example, the D in the work example, the distance represent the distance between the two plates, not in the distance between the charge particle, okay? So in the work example, the distance, the D is not the distance between the charge particle, right? It's not the charge particle to another charge particle, okay? It represents the distance between the two plates, the D. Understand that? The D is the uniform electric field. The D represents the distance between the two plates, not the distance between the charge particle, okay?
Okay.
So you understand that? So, and in the two plates, okay, in the uniform, so the uniformly electric field, okay, and we'll know it in the uniform electric field that we have.
Are you sharing screen?
Mm-hmm. Oh no, sorry, I forgot it. I will open the broadcast. Okay, can you see?
Yeah.
You see? So I plot the graph of the two plate, okay, and I refer to the D is the distance in the work example. The distance D, the D represents the distance between the two plates, not the distance between the two particle, okay, not the particle to another particle, okay.
Yeah. Okay.
Not a D, okay. And I call it D1. This is a D2, okay. And we are not in the two parallel plates that we have the same E, right? The uniform electric field. The uniform electric field, so which means that the E constant, right? I told you, right? The E is constant. Understand?
Yeah.
Okay. And here's the two parallel plates. Here are two parallel plates. And we have the equation there. The E equal the potential difference between the two parallel plates. Okay, the potential represents the potential difference between the two parallel plates. Okay, and the D is the distance between the two parallel plates. Okay, so you can see transfer. The E is the product of the potential difference is the product of the E times the D. Okay, understand
Yeah.
this?
Yeah.
And
I want to ask what the V is
the
representing.
V
Like,
the V is the potential difference between the two plates. Potential.
then why is it different for the two plate? Like, for X and Y, why is it different?
Why is it different in a charge particle?
For the X and Y, why is it different at the 2 points in the question?
You mean the V1, here's the V2, right?
No. In the question, it says there's set X and set Y, and then they have different gradient. That means they have different V.
Yeah, the different gradient has the different V.
But they're in the same. They form the same, like, two. The two plates are forming one field. And how come there's two different V?
Okay, because in the two parallel plates, and the external that we have the current, okay, the battery, okay, and the current flows. You can see the graph. The current in the closed circuit, the current flows to the positive plate, right?
Yeah.
And positive plate, and you know in the field, the positive the positive plate that produce the electric field from the positive, right? From the positive plate to the negative plate, right?
Yeah.
So the electric field lines like this, right? And every single line just parallel between it, right? Every single line just parallel, okay? Understand that?
Yeah, understand.
Okay, and you understand that if the E is constant, right?
Yeah.
The electric field constant, and here's the D. Now here's the D. The D, here's the potential. Here the V, the potential means the two plate, the difference, right? Like here's the D, like here's the V1 is V2. The D, the V, the V is the absolute value of V1 minus V2. Understand that?
Yeah.
Okay. So I mean the V. So here's the equation. The V is the product of the E times the D. And you see this right. The V1 that will with the D increase, right? The D increase with the D increase and the potential V, right? The ending point, the ending point in the field lines, okay? That will decrease, right? That's correct. Understand that? Mm-hmm.
Yeah. Oh. So there's a potential difference.
Okay, yes. And you refer to the V is the potential in every point in the field lines. And you said is right. The V is the in every point with the D increase. The potential, the point potential, that will decrease. And I mean the V, here's the V is the potential between the two plate, right? Between the two plate. The V is the difference, right? The V is the difference. Here's the difference. Okay? Understand that?
Okay.
Okay, so here's the equation. So the E is constant, and with the D increase, the absolute value of the differences of 2 point, right? The potential difference it increase, right? Mm-hmm.
So on the graph is the V the potential difference or the V on each plate?
Yeah.
Is it on the plate or is it the difference between the two plate?
It's the different. It's the different to the two plate.
But then why is there two different V's? On the graph.
Like the parallel graph, right? Electric field graph, or another one. This one and this one.
In the question, the
Okay.
work example.
The work example is referred to the two parallel plate. Okay, two parallel plate. And in the work example, in the way in the work example represent the potential difference between the two plate, right? Mm-hmm. I said suppose the left V is V1, okay? That's the side of the plate. The point potential is V1, okay? And another side plate is the V2, okay? Right? And in the topic in the work example, the V represents the difference between the V1 minus V2, okay? Mm-hmm. And we know, you said just right, with the D increase, okay? With D increase, the point, like the point potential decreases, right? This is right. Understand that? So V1 and will greater than the V2, okay?
Yeah.
Suppose the point potential, the initial value is 100, and with the D increases, the initial, if the D1, here's the 2, suppose is the 20. And if now I increase the distance between the two plates, okay, with the D increase and the potential point potential decreases. So the V2 will become the 8. Okay, so the change in the potential, right? Now the change in the potential, the V potential, V, they will become bigger, right?
Yeah.
Okay, it's just because the 100, the original value is the 100 minus the 20, but now that has changed the 100 and minus the 8, right? So in the work example, the V represents this, the change in the potential, okay? So that's the reason why the D increase and the potential difference between the two plates increase, right?
Yeah.
Understand that?
Yeah, I understand that now.
Okay, and talk about another is the point potential, okay? The point potential. The point potential refers to the ending point, like if the electric field, the field lines, and I draw from the center to the infinity, right? And suppose here's the point 1, here's the point 2, and the point 3, okay? With the increases, with the distance increases, right? Okay, the distance between the another charged particle. Okay, and I suppose the distance is d, okay, right?
Yeah.
And with the d increases and the potential V1, the point potential, suppose the point 1, the potential corresponding the potential 1. Here's the point potential, is the potential 2, okay? Here's the potential 3, okay? With the d, and the d increases, and the potential, point potential, the will decrease, right? So the V1 greater than the V2, greater than the V3. Okay, understand that?
Yes, yeah.
Okay, if I see the potential difference, in V1 to the V2, okay, and V1 to the V3, which one is bigger?
V1 to V3.
Yes, no problem. Okay, so the V1 minus the V3 is the V, the work example referred to. Understand that? Now?
Wait, no, not really.
Mm-hmm. Which point you confused? You feel confused?
Why does it connect to the V equals ED?
V equals ED, right? So you confused about this equation, right? This equation.
No, why are we doing V1 minus V2 and V1 minus V3?
Okay. I just used the minus to represent the potential difference, okay? Potential difference refer to the two-point potential difference, okay? The potential difference, okay, is the difference of the two different point potential, okay? So V1 minus V2 is means the potential between V1 and V2. So I use the potential at point 1 to minus the potential at point 2. Understand that?
Yeah.
Okay, right? And V1, I talk about V1 is the potential at the reference point, okay? The V2 and V3 are potentials at the R point and further from the negative plate. Okay. Now understand that?
Yeah.
Okay, so in the work example, here's the keywords. The keywords. If the next time you meet a new work example, if we meet the electric field, okay, the uniform electric field, that we use the formula, this one. The E equal the potential over D, right?
Yeah.
Okay, and the potential means this one and this one. This is V1, this is V2, okay? The difference between the two point potential, okay? And V equal the E times D. Understand that? And D increases, so the V is the 2-point potential, right? D increases, so the V increases, right? Understand now?
Are we moving the the charged plates? Are we moving the plates to be further away?
No?
Then what does the distance mean?
Okay, the distance means the two parallel plates. The two parallel plates. This one, this represent D, the distance. Okay, this which means the separation distance. The D is the separation distance. Okay, the separation distance between two parallel plates. Understand that?
Then how does the distance increase?
The distance increase, right?
Yeah, how?
If I set the right side plate and go further, put it this way, so I will make the D increase.
Oh, okay.
Okay, right?
Yeah. And then the electric and then the voltage, the potential difference increase.
Yes, and the E constant, right?
Yeah.
Okay, because the electric field in the environment, the kept constant, and with the distance between the two parallel plates. And you talk about if I take the right side or I use the left side to go in further, okay, or separate more further distance, okay, and that will make the distance become bigger, right?
Yeah.
Okay, and here's now the potential between the two plates that will increase, right? Okay, so you can see the graph, okay, and so the work example, the graph with the axis is the D, the Y axis is the potential. So here is the line, right? Understand that?
Yeah.
Okay, no problem. Now,
Yeah, no problem.
okay, look at the question, the homework. The first, okay, the question 1. And you can see the switch is closed. Okay, the switch is closed. So here become the charging process or discharging process.
Charging.
Charging, this one, correct. And the current will go through this one, right? The current will flow to the positive plate, right? So the process is called charging process, right? And with the charging process, the potential over the T that will increase, right? Understand that? And cross the origin, right? Start from the origin.
Yeah,
right?
yeah.
And here's the asymptote line, right? Here's the asymptote line, right? Here is
Yeah.
the approach to the 3. Okay. And the reason why you don't write it?
I don't know why.
Okay. The question just want us to explain one movement of the diaphragm causes a potential difference. The signal across the resistor R. The resistor R. You can see the diaphragm movement causes the voltage. See the graph? When the diaphragm, and we can write it in this form. When the diaphragm moves, okay, and the capacitance change or not change?
Changing.
Okay, yes, the C changes. Okay, and we can use the formula because the charge quantity, the Q equal what? Equal what? The charge quantity equal what? Equal what?
I'm not sure.
The C and V, the product, the capacitance times the potential, right?
Oh yeah.
Okay, so the charge quantity that changes, right? Because the capacity changes, so the charge quantity changes, right? Understand that? No problem?
Wait.
Because you just see the C changes, right? The C changes, the capacity C changes, right?
Yeah, the C changes.
The C changes, and the V, the V
But
is constant.
is the charge constant?
Yeah, charge constant, the 3. Understand that? So the charge quantity, right? The V, the potential constant, right? And the Q, the charge quantity, the changes, right? Understand that?
Which one is constant?
The potential V, the V, because the topic just told us the V is the 3, okay?
Oh.
Okay, so the charge quantity both changes, right?
Yeah.
If I change the capacity, so using the formula, the charge quantity, the charge equal the product of the capacity times the potential. So I change the capacity, so when the potential constant, so the charge quantity that changes, right?
Yeah, charge quantity changes.
Okay, charge quantity changes. Okay, and the charge flow through resistor R, right?
Yeah.
And so a voltage, we use the Ohm law, right? The R, the I, and times R, right?
Yeah.
Appears cross R, right?
Yeah.
Understand that? So we can write in this form. Okay? Understand that?
But when the charge changes, how's it change? Like, is it changing in the 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 capacitor?
Yeah, in the capacitor.
So it's discharging.
Discharging, not discharging.
Is it discharging? Like,
You see in the process, this process is discharging.
oh, okay.
Okay. The same, right? And this question, look at this. The circuit below model a single pack seal of the CCD device. The photo cell, here's the photo cell. Okay. The photo cell generates a voltage that depends on the intensity of the light, right? Intensity of light falling on it. When information about light intensity is required, the switch is open, okay? And the voltage across the capacitor at the instant can be read out into an electronic circuit represented by the voltmeter at a later time. And the topic, you use the formula to calculate the charge, and the Fred is right. Okay, and the mile voltage, right?
Yeah.
95. Okay, so use the right, no problem. The two, why don't write this?
Uh,
Mm-hmm.
I don't know why it stays, like, I don't know why the voltage stays for some time.
The voltmeter reached the 95 mile voltage for some considerable time. And the question, let me say what this tells you about this voltmeter. Okay, it tells you about the voltmeter. It's like for some considerable time, which means maybe the resistance is high or low. Is high or low?
Higher?
Yes. Higher, which means no current drawn, right?
Yeah.
Okay, so we can see. We can write this because this the question has the very high resistance. Understand that? Okay.
Not sure why. Why does it? Why is it? Because, like, why the high resistance causes the delay?
Look at the voltmeter. The voltmeter reads the 95 mile voltage for some considerable time. And in the topic, the circuit below, and I see the voltage across the capacitor at the instant can be read out. If I keep the voltmeter, the reading keep the 95 mile voltage, right?
Yeah.
If I keep the value. If I keep the value, which means the voltage kept constant, right? If the voltage kept constant, so which means the capacitor is charging or not charging? Is charging or not charging?
Charging?
No. Why not charging? Because there is no potential change. Why I charging? Think about it. The voltmeter reading remains unchanged, right?
Yeah.
The voltmeter reading remains unchanged for a considerable time, and that mean the capacitor hardly discharges, right? Understand that?
So
The
it charges
potential,
later?
yeah, which means the capacity hardly discharge, right?
Yeah.
Like, you think that the potential, the voltmeter reading remains unchanged, right? Remains unchanged for a considerable time. Which means the capacitor must be harder discharge, right? Harder discharge. Okay, that indicates the voltmeter has the very high resistance, right? Because if we have the very high resistance, that will result in extremely small leakage current in the circuit, okay? Right? So the charge, you think about, if the phenomenon happens, the charge on capacitor streams very slowly, right?
Yeah.
So we can keep the voltage stable for a long time. Understand that?
Okay.
Mm-hmm.
Yeah.
You think about it for this angle. You think about, if the voltmeter, if I want to voltmeter the reading, keep the constant, right? Keep the constant. Okay. So if I keep the constant of the voltmeter, the reading keep the constant unchanged, right? That means the capacitor can be discharged, right? Understand that? If the capacitor discharge, the potential will decrease, right? Understand that?
Yeah.
Okay. If the capacitor discharge the electrical energy, the potential must be decreases, right? Okay. The graph, okay? Understand that? If in the discharge process, the potential with the time increase, the potential will decrease, right? But the voltmeter unchanged, right? So the V unchanged. Okay? If the V unchanged, so which means the process is not discharged, right?
Oh, yeah.
Okay, it's not discharged. Not discharged, which means there's no current change, right? No current change, right? Understand that? Mm-hmm.
Okay. Yeah.
There's no potential change, right? No potential change, and must be no current change, right? No
Yeah.
current change, that must be that has the very high. That must be has the very high has a very high internal resistance. Okay,
Okay.
understand that? Very
Yeah.
high internal resistance. So we can see the voltmeter, they keep the constant, right, for a long time, and we can keep the voltage stable for a long time. Understand that?
Yeah.
Okay. So we use the potential unchanged to get the there's this is not a discharging process, okay? In the not discharging process, that means there's no current change, right? No current change, which means using the Ohm law, right? The Ohm law, okay? No potential change, no current change, which means that we have a very high internal resistance, okay? Understand that?
Right. Yeah.
Okay, so if we have a very high internal resistance, if we have a high internal resistance, that will result in extremely small leakage current, right? Understand that? So the charge on the capacitor drains very slowly, okay? And this is the purpose of to keep the voltage stable for a long time. Understand that right now?
Yeah.
Okay, no problem. Is there any problem? This question?
No.
Okay. And in this graph, you calculate, right? Use the discharging equation, right? And this is the graph. Okay, best field line, no problem. Here's the intersection with the y-axis, and you use the to calculate the slope, right? The gradient.
Yeah.
And the topic just want us to explain how the graph shows the voltage decrease exponentially. Okay, you see what?
The
You see
Because
what?
the ln values decrease linear, so the actual values should be exponential.
Okay, no problem. This one got the 1 mark, and the value decreased like the exponential, right? Get the 1 mark. Okay, no problem. And the question 2, find the appropriate value for resistance of the second voltmeter. How to calculate? How to calculate? You don't know how to calculate?
No, I don't know.
You have the graph. You have the graph. So how to use the graph or use the another question to calculate the graph? How to use the graph to calculate? The graph you have the intercept. The graph you have the slope.
Yeah, intercept.
Yeah, we might use the interceptor, okay? How to use the graph to calculate? The question is want us to find the appropriate value for the resistance of the second voltmeter. The second voltmeter, the resistance of the second voltmeter. Okay, the second voltmeter. How to use it? Think about it. Why?
Think we can turn it into a
We
equation?
want the resistance. We want the resistance. Resistance. You remember the time constant? The time constant? The time constant is what? It's a product resistance times capacity, right?
Oh yeah.
Okay, in here equation, that we can get the resistance, okay? Use the time constant, okay? To over what? Capacity, right? The time constant is what?
Yeah.
Time constant. Time constant. How to get the time constant? Use the slope or something else. The slope. Time constant. How to get the time constant from the graph? Time constant. Don't forget the equation. Yesterday we have learned the formula. The gradient represent what? The gradient represent what?
I forgot.
You need to write the equation form. And here's the form. The y is ln, right? The ln v, and the x is t, right?
Yeah.
And the gradient is the -1 over RC, right?
Oh yeah.
Okay, and plus the ln, right? With 0, okay? So we can use the graph you plot to get what? To get the gradient, right?
Yeah.
Okay. The gradient might use the changing in the delta y, okay? Over changing the delta x, right? Understand that? The delta y over delta x, right? To get the gradient, okay? The gradient represent the -1 over RC, right? Here RC is the time constant, right? Understand that?
Yeah.
Okay, so if I got the gradient, okay, and after that, and we can solve the resistance of the second voltmeter, right? Understand that?
Understand.
So the first step, you have to calculate the gradient of the best field line you plotted, right? And the second, using the gradient represents the -1 over RC. Okay, and the RC is the -1 over the gradient, right? Okay,
Yeah.
and take the gradient value into, and we can get the RC. Use the RC to get the resistance, right? Calculate to over capacitance, so we can get the resistance. Understand now?
How do you get the capacitance?
Capacitance from the graph. Capacitance. The top dimensional capacitance not mentioned, right? Here is the capacity, right?
Oh.
Here's the capacity, right? The
Okay.
previous topic just told us the capacity. Okay, understand that?
Okay.
Okay, and we can use the time constant to over the capacity equal 0.22. Okay, right?
Yeah.
Understand? Okay. The question 3. Use why is what? The charge is being stored in the capacitor, and this is what? And as it reaches the maximum capacity, this is what? The current decreases, right? Yes, you write it. This is the current, the word. This one is what?
Right?
The current.
Yeah.
The current decreases. And the question wants us to explain in terms of the charge, using the charge to interpret what happened in the circuit. And this is the charge explanation, right? So the capacitor in the charge process, okay. So the current that will decrease, right? Here get with the 1 mark, okay. And the curve. So here's the 3 mark. Here's we get the 1 mark, and the energy store get the 1 mark, but have another 1 mark we don't get. And you think about how to get another 1 mark. How to get another 1 mark? Another 1 mark refer to what? Maybe the shape, right? Maybe the shape of the graph, right? Because the graph is exponentially, right? Decreases exponential, right? Understand that? Exponentially. You need to write this word. The keyword is important because the another mark is for the exponentially to describe the tendency. Understand that?
Okay.
Okay, because the decreasing process is exponentially decreases, not linear decreases. Okay, so we need the word exponentially to describe the shape, decreases shape. Understand that?
Yeah.
Okay, it's another mark, so we can get the 2 mark. And explain what we have seen if he had watched the ammeter 2. Ammeter 2 is what? Ammeter 2 is right.
Yeah.
No difference because they are in the same circuit. Ammeter 2. Here's the 2 mark. Why no difference? Why no difference?
Are they not the same series?
Because the collect of the X, right? And in there's the no current change, right?
I think they should be the same.
Okay, no problem. It's the same. The Y mark, get it. And here's the no difference. Okay, no problem. And use the sketch graph to estimate the charge. Okay, estimate the charge, which has passed through the emitter 1 between the time 3 to the 10. Okay. Which formula you use? Which formula you use?
Trapezium.
The competency. This one, the charge quantity over the V, right? This one.
Oh,
Right? You should
I
use
used the graph.
this one. This one, the graph. The current, because we have the EMF is 1.5 voltage. And the charge quantity is what? Charge quantity is what? You calculate this is charge, right? So charge is the 63 mil capacitance. And the C taken into, right? And the 21 UFRAD. And the graph, okay. Oh, the charge, right? Right, yeah. Okay, use the graph is correct. No problem. Okay, understand that?
Yeah.
And another one. Use the graph you answer above the estimate. The capacity. So the 4.2 is over 1.5. The battery, look at the EMF is what?
0.5.
No, it's 3 because each cell, there are 2 cell. Look at the one cell is 1.25. This one is 1.5. So together, it's 3. Understand that? 3 voltage.
Yeah.
Okay, because the topic tells each cell has the EMF of 1.5 voltage. So this cell 1.5, another cell is 1.5. So together, the total EMF, the total potential, right, have the 3 voltage. Okay, so we have to change the 1.5 into the 3. Okay, understand that?
Okay.
So the answer is what now?
2.1.
Okay, 2.1. Okay, so be careful. Look at the keyword, right? This one. Understand that now?
Yeah. Okay. Got it.
And stay. Okay, stay. Get 1 mark, and explain. Get another mark. And stay and explain what he will observe each emitter if he then continue the experiment by moving the collection X from L to the M. Okay, from L to the M. You don't understand this topic? The question? From
I
L.
know that the EMF is now 3.
So the X is from L to the M. Okay? So what changed? What will change?
The EMF increased to 3.
Okay, yes. So the current has the opposite direction, right? Opposite direction, right?
Wait, what?
So the current has the opposite direction, right? For the A1.
Wait, why?
Because if you collect this one, collect this the point, if the A2 switch to the M from L, and the current, right? The current for A2, what will change? The current, what will change?
Double?
Why double?
Because EMF is doubled.
Let me think. If I switch from X to the M, if I switch to the M, and what will change? And here's the line, right? Here's the line. And this is the current from the current flows, right? To the M of the, what is the M? Think about it. When the X moves from L to the M, the battery might reverse, right? The battery is reversing the circuit, okay? Understand that?
No, I don't know why it reverse.
Because the point has changed. The current, they change the direction. Like this one, okay? This one. So the energy flows, right? Flows from this point, okay? Understand that?
But the direction of the battery didn't change.
But if I collect another point from M, from point L, they create a net voltage, right? Create a net voltage. So right now, because the M is not battery, okay? Because in the circuit there's no battery. This will be cancelled. If the point switch to the M from L, okay, there's no battery right now, and the capacitor will become a new battery, okay? Understand that? Become a new battery, and this process is the discharging process. Understand that? If the discharging process, so the current will flow in this way. Understand that? Flow to the emitter one.
Wait, why?
So
Why is the battery not there anymore?
because the point connect to the M. The point connect to the M.
But then it's still in the circuit.
No, you look at the question. The observe if each emitter, if we continue the experiment by moving the collection X from L to the M, and this process will become the new process. The process is discharging, not charging process, which means that we have reached the maximum of discharging, right? And it that becomes the discharging, right? Not charging. So we can regard the battery is not in the circuit, okay? So the process will become discharging, right? So when discharge the energy, the capacitor will become the cell, okay? And the energy, the current that flows like this way, right? Understand that?
Okay.
Mm-hmm. Understand that?
Yeah.
So the emitter, right? So emitter one. So emitter one that has the large current right now. Yeah. In the opposite direction, right? Understand that? Okay, this is for emitter one. Understand that?
Yeah.
Okay, and how about the emitter two? Emitter two. Emitter two, it become what? Mm-hmm. Emitter two. Emitter two. Emitter two. How to describe emitter two?
The same.
Is the same with the emitter one.
Yeah.
Why? Because in the circuit, right? The emitter two, the same, so can describe in this way. Same current as emitter one. As emitter one, okay? Because this is the series circuit, right? Understand the series circuit,
Yeah.
right? So we have the same current as the emitter one, and so it also shows a brief, right? Brief reverse current. Okay, understand that?
Yeah.
Okay, right. So we finished the question 3. Okay, the rest of the question you didn't work.
I didn't understand.
Okay. Next lesson, I will talk about the rest of the questions, and we are continue to learn a new chapter really about the magnetic field. Okay.
Yeah. Okay.
So next time, what is time you're available?
Monday.
Okay, no problem. And you can use this notebook, and I send you can use the what I have learned to interpret the question, and use we have learned in the question to retake or to think about this question. Okay.
Okay. Yeah.
Okay, I will send you. Bye bye.
Okay. Thank you. Bye bye.
Bye bye.
Tomorrow we will be studying until I pass out. Period. I'm gonna go eat dinner now. God damn, that's a lot of money. 816 $1,000 in Hong Kong. Lucky horse betting. Oh, your man does not want to do this, mate. More man. Do they have wings here? I want to do this. Whew. I do not want to fucking study. 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 Oh. Want some low cortisol fights, not this bullshit. was no chance. What happened to this? I can't beat that guy. Cortisol. Actually, this guy might be good. He went after me. My god, not fast enough. Low cortisol. Low cortisol. Studying until I finally collapse. God, I'm tired. The most insane stream ever. God, I'm tired. God, I'm tired. Whew.
Potential. It's like a voltage, right?
Yeah. Yeah.
Potential.
Yeah.
What is the definition of potential?
The joules per coulomb.
Joules per coulomb. Maybe you can use some other words to describe it. Maybe you can use some formula. I don't remember the formula. And the last lesson, I just used the equation and the energy, electrical energy equal the charge times the potential difference, right? The potential, okay? Right?
Yeah.
And the potential, that is the electrical energy over the charge quantity, right? So we can use the fraction to define the electrical potential, right?
Yeah.
It's like electrical energy per unit charge, like electrical energy per the charge, right? Okay. Understand that?
Okay. Yeah.
Okay. And the next formula, that's a 7.6. The electric field between the parallel plates. in the parallel plate, what we will produce in this environment?
Uniform
Uniform, yeah,
electric field.
yes, the uniform electric field, just like in the environment, right? And everywhere, every point in the environment, we have the same direction or same magnitude of the electric field, right? Like here's the two parallel plates. Okay, maybe we can suppose the left one is a positive, and the right one is a negative. So we can draw the electric field lines, right? Like this. Every single lines and parallel, right? Okay, and in this distance, right, in the two parallel plates, we have the same E. The E, that's the electric field, and the everywhere in point, okay, the every in point, we have the same magnitude and the direction. The direction is from the left to the right, right? Left to the right, the electric field. Understand that?
Yeah.
Okay, and then the final one is the 7.7. It's about the electrical potential for radio field. Radio field. The radio field, maybe we can use the two different charges. Like if we want to draw the positive charge and put it left side, and put the right side and negative. Okay, and we just want to draw the radio field, and how to draw it? The left one is the positive charge, and the right one is the negative charge. Okay, how to draw the radio field? How to draw it?
The middle is the straight line.
Yeah, it's straight line. From the direction, just from somewhere to another where?
Positive to negative.
From the positive to negative, right? Okay. Yeah. Okay, the arrow, how to label arrow?
In the middle.
Okay, right. And another line like this, right?
Yeah.
Okay, so these are two different charges that produce the electric field lines, right? Okay, now, and how about just one single positive charge? The one single positive charge, then positive will produce the electric field, the radio field, like this, right? From the center of the positive charge to the infinity direction, right? Okay, and in purpose to the more, and we can draw just 1, 2, 3, and 4, and 6 lines, right? Probably you can just draw the 6 line, right?
Yeah.
Okay, and how about the negative one? Negative charge, how to draw it?
Towards the middle.
Okay, towards the middle, just from the infinity to the center, right?
Yeah.
Okay, so that's the 7th chapter. Is what I have learned about the electric field. In this chapter, we have learned the formula how to define electric field and how to calculate the electric field strength. Okay, and we also learned the force that we call the Coulomb force, right? Okay, and the 7.4 is about due to the point charge, how to draw the electric field. And another, we have also learned the potential. And finally, the parallel plates produce the uniform electric field, right? Got that?
Yeah.
Okay. After that, we can take some exercise. Okay, I will pause. Wait for a second. I'll pause. Okay. Can you see the board?
Yeah.
Okay. Let's check the exercise we did about the electric field. And look at either one. Okay. This is the option, the multiple choices. The force between the two identical point charges x, y, and its force is F. Charge x is double. Charge y remains same. And we just want to know which row of the table gives the force on each charges. Okay, choose which one. A, B, C, or D.
Think D.
Why? Give me the reading.
Because the force on each side should be the same, and then in the formula, if x is doubled, then the entire formula is doubled.
Okay, no problem. Okay, next one. The medium question. The distance between the proton. Okay, the proton is just the charge that is positive, right? Positive.
Yeah.
Proton has a positive charge, and the electron.
as we're earning millions of dollars, I don't think it's important that we're getting copyrighted. It's the 2 songs from the Invincible episodes we watched. That's it. Let's continue studying until we collapse. Hey! Why are you on my account, boy? Hey! Can't believe it. Oh. Boy!
The radius between is the R, the electrostatic force. Okay, I have a question. What is the types of the electrostatic force? Include this.
The distance between the proton and electron is R. The electrostatic force is F. The distance between the proton and electron is doubled. Which of the following equal to the electrostatic force at this separation? F over 4.
Electrostatic force include this what force?
I don't know.
Attraction.
Oh, and repulsion.
Yeah, repulsion. Okay, the two types are included in the electrostatic force, right? Okay, the distance between the proton and electron is double. Which option is equal to the electrostatic separation? Choose which one. Maybe we can use Coulomb's force, the formula.
Yeah.
So use the formula. The final answer
Is D,
is D. Why D?
because the distance is doubled and distance is squared, so it's 2 squared.
Because the radius is the denominator, right? Double the
Yeah.
denominator. Okay, and R squared will be the 4, right? And will be 4, so the factor will be 1 over 4, right?
Yeah.
Okay, so the final answer is right. Okay, look at the question 2. A potential difference is applied across the two parallel plates. A particle carrying a charge of the 0.1 coulomb is placed between the plates and experiences a force. The distance between the plates is halved, and the potential difference remains constant. Which of the following is now equal to the electric field strength between the plates? Okay, the question just wants us to calculate.
Potential difference is applied across two parallel plates. A particle carrying a charge of 0.1 is placed between the plates and experiences a force F. The distance between the plates is halved. The potential difference remains constant. Which of the following is now equal to the electric field strength between the plates? So the electric field strength is now... Oh, this one is hard. This one is hard. Oh man. Bro, I don't fucking know. I simply don't fucking know. I don't fucking know. I don't fucking know. Distance is halved. I'm gonna need him to tell me
The
the
electric
answer.
field strength. So maybe we can use the electric field strength formula. How to calculate? Electric field strength, the formula. Just now I have to ask you to tell me the formula. Electric field strength.
Equals F over Q.
Yeah, it's F over Q. And another form. How about another form?
Electric field strength.
F is Q1, Q2.
Yeah.
Over R squared times K.
Okay, maybe we can use the Q1, right? Or Q2, right? R squared and over the Q1, right? So you find out those Q2 over R squared. Or maybe the two form, right? And you just look at keyword, the distance between the plates, So the phenomenon is really about the two parallel plates. Two parallel plates will produce the uniform electric field, right?
Yeah.
Okay, so if you want to calculate the uniform electric field, so maybe we can use another formula. Is what? I remember the two parallel plates. Okay, and the two parallel plates has the potential V, right? And the separation distance we call it D, and this one, the uniform electric field is E, right? So construct the equation, the E equal to the potential difference over the distance, right? Okay.
Yeah.
We can use this one, right? Okay. So if we use this one, and so which answer is right? Which choice is right? Okay. How to calculate?
Electric field strength.
Think about it. The two parallel plates so have the uniform electric field strength formula, right? The E equal the potential difference over D. Okay. And besides, the force equal the charge quantity, the charge times the electric field strength, right? Okay. And we can see the topic to us the big information that is the particle carrying a charge of the 0.1, right? 0.1 quantity. So we know the Q, right? We know the Q equal 0.1, right? Right?
Yeah.
Okay. And we can use the force equal the Q times E, right? And we know the Q, that is the 0.1. So the E equal the force over Q, and the force over, take the value into the equation, 0.1, right? So the value will become the 10, right? 10 F, right?
Oh yeah.
Understand that? Okay. This step. And the distance is halved. Distance halved. And the distance halved. So the uniform electric field will change or not? The distance is halved.
Yes.
Right?
The
Okay. So the electric field strength will becomes double, right? Will become double.
We're not finding the force, we're finding the electric field strength. Oh my god, this is so hard.
of the original one, right? Okay, the E1 will become the double original one, right? Because the
Okay, Bane. I get it. I get it.
potential different constant, and the distance becomes half. So substitute d over 2, right? So the value will become the 2 times d over d, right? Understand that? So it becomes the double e, right?
Okay.
Understand this step?
Yes, yes.
Okay, so finally, we can use the new electric field strength and the force. Okay, use the new electric field to calculate, right? To calculate the E, right? The E is the double times the original one, right? The original one is the turn F, right? Is the turn F, right? Original one is the turn F, right? And substitute, right? So the final answer will become the 20F. Understand that?
Yeah.
Okay, so and I need you to tell me how to calculate the final result. Use what we have right on the board information. So tell me the first step, what we need to do. The second, the third, the final answer, how to calculate it.
Use the use the E equals V over distance first, and then distance is halved, so the new E is 2E, and then use E equals F over charge, and charge is 0.1, so the E is 10F, but because the new E is 2E, then 10 times 2 is 20F.
Okay, right, the problem.
Yeah.
Okay, so the first step, you just calculate the original one, the original electric field strength, right? That is the 10F. Okay, and due to the condition has changed. That is the distance between the plates is halved. So the electric field strength will become the double, right? Will become double. And the original one, that's the 10F. Okay, so now becomes the double. So will be the 2 times the 10F, right? So final answer will be the 20F. Okay, so choose the option C, right?
Yeah.
Okay. Understand that?
Yeah, understand now.
Okay, right. And okay, here's the 2 plates at the point X. Experiences electric force. Okay, but the 2 points X and Y at different position. The electron moves to point Y, which is halfway between the point X and the left hand plate. Which of following is the electric force experienced by the electron Y? Okay, use the information how to analyze it. Think about it and just tell me. And tell me how to use the information. 2 plates. Okay, 2 plates. And experiences the electric force. And the electron. Okay, here's the particle electron. That's the negative. Move to the Y. The position Y point Y is half. Okay, it's a half. It's a half between point X. Okay, so the distance is half. The point D is the middle. Okay, and which of following is the electric force experienced by the electron and Y? Is what?
I think no difference.
No difference. So the final answer is B, right?
Yeah.
Why?
Because the distance between the plates did not change.
Okay, yes. So you just
God damn it! I was thinking about formulas. As simple as the fact that it didn't change because every point in the uniform electric field has the same electric field strength and therefore the same force. As long as the charge is the same. Right, makes sense.
The electric field strength is not changing, right? Because the two parallel not changing, right?
Yeah.
Yeah, the two parallel plates not change. Okay, so the electric field strength unchanged, right? The E is same in everywhere, right? And we know it. The force is always the E times the charge quantity, right? Okay, and the E electric field strength unchanged, and the charge quantity, right, not changed, right? So the final answer is not changed, right? So choose the option B. Okay, understand that?
Yeah. Okay.
And look at the hard one. The graph shows how the electric potential V varies with the distance x, and which of the following shows the correct.
Electric field strength E with X. Electric field strength is V over X. V over X is... V is negative change. X is positive change. So it's negative gradient that's constant, so it's B.
Corresponding variation of electric field strength with x. Okay, the graph. Mhm. We need to find the potential and access to know what Mhm. From the graph the voltage over x graph. What we can learn from it? What we can know? The gradient, the area, or something else? Written in the electric field strength. Choose which one.
Sure.
Have you
B.
ever remembered the formula? The electric field strength equal what? The friction equal what?
Electric field
V.
strength
The
equals
potential difference over d, right?
potential,
is the distance.
electric
Okay, the
potential
distance is
over
the x, right?
distance.
Yeah.
God
Okay,
damn
and
it.
the potential is the y-axis, right? Is the
Yeah.
y-value. Okay, so which means the E is the slope from the graph, right?
Oh.
Or gradient graph, right? The gradient.
Okay.
Mhm.
Then I think it's B
Okay, the YB, the below the graph.
because
The
the
gradient is negative or positive.
negative.
Okay, negative. So choose the option B, right? Bingo. And so the exercise is done. Okay, and let's come to a new chapter. Last lesson we have just learned the electric field, and this lesson we're going to learn the capacitance. Okay, have you ever remembered the capacitor? What is the capacitor? Capacitor. What is the capacitor?
Forgot.
Forgot, right? Okay, here's capacitor is always the electric devices. We always use it just a tool to store energy, to store energy, the electrical energy. And the voltage is the 7.9. Understand it right now?
Yeah. Yeah.
Okay, so okay, and second, how to understand? So we can call the two parallel plates
People are checking out my stream. Oh, so tired, man. So tired.
Okay, so
Capacitors are electrical devices used to store energy in electronic circuits. Revision questions. Commonly for a backup release of energy if the power fails. Capacitors do this by storing electric charge, which creates a buildup of electric potential energy. They are made in the form of two conductive metal plates connected to a voltage supply. Two conductive metal plates connected to a voltage supply. Parallel plate capacitor. There is commonly a dielectric in between the plates to ensure charge does not flow across them. The capacitor circuit symbol is this. The capacitor circuit symbol is two parallel lines. Capacitors are marked with a value of their capacitance. Capacitance is defined as the charge stored per unit potential difference between the plates. Charge stored per unit potential difference. That's really hard to understand. The capacitance of a capacitor is defined as the equation capacitance equals charge over potential difference. Unit charge per unit potential difference.
sometimes we also use the tool to store the energy, and after we store the energy, maybe sometimes we can use it to discharge the energy, right? Okay, so here we have the two processes with the capacitor. The first process, that is, we can use it to charge the capacitor, to charge the stored energy, right? The electrical energy. And after we have charged the energy, and we can use it to use the electrical energy. Maybe sometimes we can use the capacitor to discharge the electrical energy. Okay, so we have the two processes, right? Understand that?
Yeah.
Okay, so capacitor we can use to store energy, or we can use to discharge the energy, right? And the symbol is like this: the two parallel plates. But I have a question: is there any current in the middle? In any current in the middle?
Yes.
No current, because we don't need any of the current to pass from the left side to the right side. Okay, there's no any current, right? Understand that? Okay. So the charge process like this. I will plot the circuit. Plot a simple circuit. Okay, the battery and the current goes like this, right? And from positive to negative. Okay, and the current goes like this to the plate 1, right? The left plate. Okay, and to the left plate we call it positive. But the left is the negative. Okay, but there's no current to positive, right? No current. Okay, understand it, right? Okay, and we want to use a Phillips quantity to describe the how strong or how the ability is strong, or the capability or capacity of the capacitance. Okay, and we always use the capacitance to describe the capacitor. Okay, and here's the formula to describe it. If we want to use the
Capacitors are marked with the value of their capacitance. Capacitance
to charge the quantity, right? To charge the quantity. And the symbol C is the capacitance. Okay, the capacitance is the definition that the charge stored per unit potential difference, right? and it's the charge quantity, okay, and over the potential difference, right, between the two plates, right? You understand that?
Okay.
Okay, this is the first formula we have learned. Okay, if you want to calculate the capacitance of the capacitor, okay, the first step or first equation we need to think about use this formula, okay? The C equal the Q over V, right? Understand?
Yeah.
Okay, and which means the charging quantity is Q equal the capacitance times the potential difference between the two plates. Okay, the potential difference. Okay, the potential difference is the battery potential difference, right? Understand that?
Yeah.
Okay, and the unit. Remember the unit. The capacitance unit is F. Okay, not force. The unit is F. Okay, understand that? Is there any problem?
No.
Hello.
Yeah, no problem.
Yeah. Okay, and look at for example, a parallel plate.
Farad. Reading this is really confusing, but it also explains why the current changes direction. This capacitance equation shows that an object's capacitance is the ratio of the charge stored by the capacitor to the potential difference between the plates. An object's capacitance is the ratio of charge stored by the capacitor to the potential difference between the plates. Stored by the plates. A parallel plate capacitor has the capacitance of 1 nanofarad and it is connected to a voltage supply of 0.3 kilovolts. Calculate the charge on the plates. So it's charge over voltage. Wait, is it? Charge over potential difference, yes. So 1 times 10 to the negative 9 equals charge over 0.3 times 10 to the negative to the power of 3. Talked a lot about Dragon Ball. Oh shit, our bitrate is booming right now. Crazy. Parallel plate capacitor. Yeah, we already calculated that.
Capacity on the plate. Okay, how to calculate? The answer is the C capacitance, right? Equal. The charge quantity over V, right?
Yeah.
And we know the information of the C, right? Capacitance.
Yeah.
Capacitance is the 1 times 10 to the negative 9, right? Okay. And the charge quantity we don't know, right? And we will calculate the charge. And the potential is what? Potential.
0.3 times 10 to 3.
or maybe you can write the 300, right?
Yeah.
300. Okay, so the Q, the final equal, the C times V is the 300 and times 1 times the negative 10, right? So
Yeah.
maybe you can use the 3 times and 10 and negative 7, okay?
Yep.
Q equals CV, yes.
The unit is what? Physical unit is what? Of charge.
Micro.
Micro, the C, right?
Oh,
The unit.
Yeah.
Okay, C, right?
Charge.
Okay.
Coulomb.
After that, okay, and after we have now the capacitance is what, and what's the definition of the capacitance? Okay, and how to copy the electrical charge quantity, right? And we need to copy the energy. Okay, the electrical energy use the capacitor. If we want to charge a capacitor, so we need the power supply. Like power supply, the process just like the power supply pushes electrons to one of the metal plate, right? And in this process, the wheel does the work on the electrons, so they will produce the electrical energy, right? Understand that?
I did not pick up any of that. Entertain me, chat. Entertain me. When charging a capacitor, the power supply pushes electrons to one of the metal plates. It therefore does work on the electrons and electrical energy becomes stored on the plates. The power supply pulls electrons off of the other metal plate, attracting them to the positive terminal. This leaves one side positively charged while the other side becomes negatively charged. Hence, in this way, charge is stored by the capacitor. Pulls electrons off of the other metal plate, attracting them to the positive terminal. Gradually, the stored charge builds up. Adding more electrons to the negative plate at first is relatively easy since there is little repulsion. As the charge of the negative plates increases, i.e. becomes more negatively charged, the force of repulsion between the electrons on the plate and the new electrons being pushed onto it increases. This means a greater amount of work must be done to increase the charge on the negative plate, or in other words...
Okay, so in this process, the main target is to produce the electrical energy used the capacitor. Okay, look at the formula.
In other words, the potential difference across the capacitor increases as the amount of charge increases. This is really hard to comprehend. Negative plate, positive plate, force pulling electrons away, direction of electron flow goes from positive to negative. The negative plate, other electrons on the plate repel this electron, force pushing electrons. As the charge on this plate increases, more work needs to be done to push more electrons. So the work done per unit charge increases, so the potential difference increases as more charge is stored. As the charge on the negative plate builds up, more work needs to be done to add more charge.
Or look at the graph. Okay, so you can see there's no any removal of the electrons, right? So there's no current line in the process. Okay, so that's the reason. And look at the formula. The formula is the equation for energy stored. Okay, if just the topic just asks you to calculate electrical energy and to tell you the charge
alternative equations for the energy stored. The energy stored by a capacitor is given by energy equals 1/2 charge V. Better write this down. Accidents. It's V over Q, Q over V.
If you want to copy the electric energy, so there are two forms for us to choose it. If
To CV
if
squared.
the topic provides more information about the potential difference or charge, so we can choose the first one, the 1/2 and times the product of the charge quantity and V, right? If the topic tells us more about the capacity, right, or potential, then they probably prefer to use the second one, right? Okay, understand that? Is there any problem? Hello?
No,
Can
no
we-
problem.
Okay, to use it. So another form can write like this. Okay, look at the example. The topic just want us to copy the change in energy stored in the capacitor of the capacity. Okay, so capacitor here is the capacity. The U fret is what? Transfer into the fret. How to transfer?
Calculate the change in energy stored in a capacitor of capacitance 1500 microfarad. When the potential difference across the capacitor changes from 10 volts to 30 volts. Calculate the change in the energy stored in a capacitor.
times 10 to negative 6.
And when the potential difference, of course, the capacitor change from the 10 to 30. Okay, so we want to, and the potential. So choose what? Choose which one?
The 1 over 2 CeV squared.
Okay, right. Like this, right? Like this, right?
Oh yeah, the top one.
Okay. 1 over 2 and 1,500 of the 1 times negative 6, right? And times the changing voltage is what?
So 20.
Yeah, 20, right? The final minus the initial, right? The 20. Okay, the 20 square. Okay, and the answer will be the 20 square is the 400, right? And over 2 is the 200, right? Okay, and use the 2 to cancel. That's the negative 4, right? Okay, and the 2 times the 1,500, that is 3,000, right? And times the 10 and negative 4, right? The final answer is 3 times of the negative 1. Okay, understand that?
Yeah, okay.
Right? Okay, no problem. And
What?
there is 3 times of the negative 1. Okay, understand that?
Yeah, okay.
Right? Okay, no problem. And after we have now the two equations about the stored energy and capacity, okay, and we just want to use the graph to plot the graph or produce the graph, and we will choose the charge quantity, the charge. As the x-axis and the potential as the y-axis, and so we can use the equation, right? Use the equation. Equation V equal C times this the y-axis, and so we can use the equation, right? Use the equation. Equation V equal C times the C is the C, right? C is what? What can we get from the graph to get C? We know the charge quantity equal C times V, right? This is the x, and this is the y. So from the graph, we can plot the linear graph, right? And what can we get? How to get C from the graph? How to get the C, the capacities from the graph?
V over Q equals 1 over C.
Or maybe the reciprocal of the gradient, right?
Uh,
We can regard as the V as y and regard as the Q as the x, right? So
Yeah.
the gradient is 1 over capacity, right?
yeah,
So
yeah,
the reciprocal of gradient represents the capacity, right?
yeah.
Yes, the 1 over C is a gradient. Is a gradient. Okay, so C might be the 1 over gradient. Okay, understand that?
Understand.
Okay, no problem. And if I want to get the stored energy, how to use the potential difference over the charge to get the stored energy, electric energy. How to get it? Use the another information. If I just want from the graph to calculate the stored energy, only use the graph, the stored energy. The stored energy.
1/2 VQ. Why though?
Think about the area. Think about the area. Think about the area. Reference what?
1/2 QV.
Yeah, the area is the QV, right? Okay, so this is the stored energy, right? The E, right?
Yeah.
Okay, so if we got the potential difference versus the charge graph, so we can use the area of the triangle, right? The area of the triangle. Use the base times the height, right? Times base height over 2 to solve the stored energy, right? Okay. Understand that?
Yeah. Okay.
And look at the for example. The variation of the potential V of the charged isolated metal sphere with the free charge Q is shown on the graph below.
Variation of potential V of a charged isolated metal sphere with surface charge Q is shown on the graph below. Using the graph, determine the electric potential energy stored on the sphere when charged to a potential of 100,000 volts. So we get 100,000 here. Find here 1 point something microcoulombs. 1/2 VC.
Use the graph to determine the electrical potential energy stored on the sphere when the charge to the potential of the 100
VQ.
and K voltage. Okay, just let us to use the graph and determine the electrical potential energy. Okay, how to calculate? How to calculate? How to determine?
100. Find the Q. So 1.
The electrical energy potential is 100.
So,
Charge to the 100 K voltage. So which segment of the area? And to find the area, right? The area represents the electrical potential energy stored on the sphere, right? Charged to the potential of the 100 K voltage, right? No problem?
Yeah.
Okay. And so we use the graph to
The electric potential energy stored is the area under the graph. The area equal to right angle triangle, so can be calculated with the equation. Substituting in the values give this.
calculate the stored energy, the electrical potential energy, right? So they always use the triangle area, right? Triangle area, okay? So 1/2 and times the base and height, right? Okay. Understand that? Okay. And just the proofs I have mentioned, the capacitor has the two functions. The first function is the charge, right? Is applies, is charging, right? Okay. The second function that is the DC charging, right? So we have the two different curves. The first curve is the charge, right? Charge. And the second curve that is the discharge, right? The opposite, right? Okay. And the capacitor are charged by the power supply, or maybe sometimes the
Capacitors are charged by a power supply.
capacitor can be a power supply, right? To charge the other appliances, right? Okay. Understand that? Okay. The way to invest.
When charging, electrons are pulled from the plate connected to the positive terminal of this power supply. Hence, the plate nearest to the positive terminal is positively charged. Oppositely, electrons push onto the plate connected to the negative terminal. Hence, the plate nearest to the negative terminal is negatively charged. I'm going to draw this out.
Other appliances, right? Okay. Understand that? Okay. The first the way to investigate the charging process. Okay. Here's the charging process. Charging process. Okay. Charging process. Okay. The charging process look like this. I plot a graph. The charging and the currents that pass through from the positive and to the left side of the capacitor, right? Okay, right? Okay. And the current passed to this one positive. In the process we call it charging process. Okay. Another discharging. That might be we have used up the electrical energy of the battery. Okay. And the capacitor.
You can't really tell I'm muscular on this GIF. I have one live viewer. That's me, I think. Electrons are pulled. Then pushed onto the plate, making it negatively charged. Charging process.
The capacitor has become the new battery, right? So the current is discharging. And current will pass through from the left capacitor of the capacitor. Okay. And pass through to the original battery, right? In the new process we call it discharging process. Understand that? Look at the graph. Hello? Understand that?
Yeah.
Okay. Okay, no problem. And look at the graph. Here is the main different graph. The first graph is about the current versus time graph, and the voltage time graph, and the charge quantity the graph. So you can guess what? The three graphs is the charging process or discharging process. The three graphs. The current versus the current over time graph, voltage.
Okay, let's try and explain this. Initially, there's little charge repelling the negative electrons from getting onto the negative plate. So it has a small potential difference in work. Then it slows down as more charge is repelling the negative electrons. So it slows down, but more potential difference, more work has to be put to further charge the capacitor. And as the charge is more filled, it is harder to fill to charge the capacitor, and so the current slows down.
Over time graph and charge over graph. The three graphs is relay about the charging or discharging process.
Yeah.
Is the
charging,
right?
Yeah.
Because we know that in the charging process the current will decrease, right? Because the battery constantly losing the electrical energy, right? So the current will decrease, right? Okay, understand that. So the curve the will decreases, right? Exponential decreases, right? Okay, because the current is the battery, the current of battery. Okay, understand that. So why the reason the current curve becomes exponential decrease, right? Okay, in the charging process. And I want to know why the potential and the charge quantity, why the potential and the charge will increases. Why? Why the curve like this increases, not like a current graph exponential decreases?
because it's building up the charge.
Okay, no problem, right? Because the
building up the charge and the negative terminal becomes more negative, which repels the electrons more strongly.
Because we have transferred the electrical energy from battery to the capacitor, right? So the potential difference of the capacitor will become, right? Will become, okay, will increases. And the charge quantity will increase, right? Okay, understand that?
Yeah.
Okay, so from the graph, we can get the key features. The key features, the first one, the shape of the potential difference and charge against the time graph are identical, right? Because they are increasing constantly, right? Because we are charging the capacitor, but the current against the time graph is exponential decay curve, right? Okay.
The current against time graph is an exponential decay
Okay.
curve.
And because the initial value of the current start on the y-axis and the decreases, the shape is like exponentially, right? Understand that?
The initial value of the current starts on the y-axis and decreases exponentially.
Yeah.
Okay. And the potential and charge will start from
The initial value of the potential difference and charge starts at 0 up to a maximum value.
the origin to their corresponding maximum value, right? Maximum
Okay.
value. Understand that?
Okay. Yeah.
Okay. The final part is about really about the discharging curve. Okay. The discharging curve is like it's like charging. It's like discharging the energy transfer from the capacitor to the other, right? To other location, right? So the capacitor are discharged. The capacitor are discharged through the resistor. Okay. And no power supply present, and which means the electron now flow back from the negative plate.
Taking a break. Capacitors are discharged through a resistor with no power supply present. The electrons now flow back from the negative plate to the positive terminal of the power supply until there is potential difference across the capacitor plates. Charging and discharging is commonly achieved by moving a switch that connects the capacitor between the power supply and the resistor.
The positive terminal of the power supply until there is the potential differences across the capacitor, right? Understand that?
The electrons now flow back from the negative plate to the positive terminal of the power supply. The positive terminal is on the other side. Charging and discharging is commonly achieved by moving a switch. Yeah.
Okay, look at the three graphs. That's it.
Wait,
The
what
difference
was that?
across the capacitor, right? Understand that?
Yeah.
Okay, look at
When the switch is connected to P, the capacitor is charged by the battery. Oh. When the switch is connected to Q, the capacitor discharges through the resistor. The microammeter records a large current which gradually decreases.
the three graphs.
The microammeter records a large current which gradually decreases.
Like this. So the three graphs
Okay, whatever.
are identical, right? The current time graph exponential.
I'm so tired. So tired.
Decay curve, right? The potential time graph decay, right? And the charge time graph. Exponential decay curve, right? So the three graphs are those. They are all exponential, right? Decrease. Understand that?
Exponential
Because
Why is
decay.
the current exponential decay?
Exponential decay is like the curve that has the more rate of the decreasing rate. Understand that?
Why is it increasing rate?
What?
Why is it decreasing faster and faster?
Because the look at the graph. In a circuit, the external circuit, we have a resistor, right? We have a resistor, right? The
Yeah.
R. Okay. The resistor that will dissipate the energy, dissipate the electric energy, right?
Yeah.
Okay. So the current will constant goes from the capacitor, right? So will decrease, right? And that will dissipate by the current or by the resistor. So why the curve will become exponentially decay? Understand?
Okay.
Okay. That's the reading. Okay. This is right. And that will the current will constant goes from the capacitor, right? So will decrease, right? And that will dissipate by the current or by the resistor. So why the curve will become exponentially decay? Understand?
Okay.
Okay. That's the reading. Okay. So the final we can polygraph the three graphs, the current time graph, the voltage time graph, the charge time graph, like the exponential decay, because the external resistor has the more rate to dissipate the electric energy. Okay, considering the resistor. Okay, understand that?
Yeah.
Okay. The key features of the DC charge graph are the shape of current, potential difference, and the charge against the time graph are identical. Okay, and the every graph are just you mentioned that exponential decay that has the decreasing gradient. Okay, and the initial value from the some initial value start from the y-axis and decreases the exponentially, right? And look at it, the rate which a capacitor discharges depends on the resistance, right? So the main reason depends on the resistor. Okay, if the resistance is high, okay, the current will decrease more slowly, and if the resistance is low, okay, the current will decrease quickly. Understand that?
Okay.
Yeah. Okay.
spend the final hour studying as much as we can. Initial value is equally called IVQ, respect to the start on the y-axis and decrease exponentially. The rate at which the capacitor discharges depends on the resistance of the circuit. If the resistance is high, the current will decrease more slowly and charge will flow from the capacitor plates more slowly, meaning the capacitor will take longer to discharge. If the resistance is low, the current will decrease quickly and the charge will flow from the capacitor plates quickly, meaning the capacitor will discharge faster. Make sure you're comfortable with sketching and interpreting charging and discharging graphs, as these are common exam questions. A quick summary to help you remember. Discharging curves are all identical. Current decreases for charging curve, but increases for potential difference and charge stored. Alright.
So this is the latest lesson we have learned, okay? And after class, I will send exercise in our level 6 group, okay?
Okay.
And this is your homework, okay?
Okay.
Okay. I will send the notes to the group.
Okay.
Today's lesson is over. Okay. Bye.
Okay. Bye bye. Thank you.
Bye.
Study chemistry.
Okay. Let's take a review of the last two lesson, right?
Yeah.
Okay. Look at the syllabus, and let's take a quick review. Last two lesson. The first lesson we talked about the electric field, right? Okay. And the second lesson we talked about capacitance. So, what is the capacitance? Remember? What is the capacitance?
Charging or discharging.
Okay, yeah. You just mentioned that they have the two processes, right? The first process is the charge the energy, right? Charge the capacitor energy, and the second process is the discharge the energy, right? Okay, and we have learned if we charging or discharging, then we have the three different graphs, right? The first graph is the current.
Accumulating charge. Accumulating charge for later use is the definition of charging capacitance. Store energy in electronic circuits, commonly for a backup release of energy if the power fails. Capacitors do this by storing electric charge. Capacitors are electrical devices used to store energy in electronic circuits, commonly for backup release of energy if the power fails. Capacitors do this by storing electric charge, which creates a buildup of electric potential energy. They're made up of the form of two conductive metal plates connected by to a voltage supply. There is commonly dielectric between the plates to ensure charge does not flow. Dielectric, I assume, is an insulator. The capacitor circuit symbol is that. Capacitors are marked with the value of capacitance. Capacitance is defined as charge stored per unit potential difference. So capacitance is charge per potential difference.
Related about the current. Second graph is related about the potential, right? Potential difference. The second and final one is related about the quantity, right? Charge quantity. Look at this. Okay, the three graph, right? Okay, and you can tell me the three graph is the process charging or discharging.
This is
Is it charging or
Discharging.
charging.
Oh,
Discharging.
charging.
Discharging. Why discharging?
No, not discharging. It's charging.
Okay, it's charging, right? Because we can see, and if the battery charging energy, right, charge the capacitor, okay, and we know the current will decrease, right? Will decrease like exponential decrease, right? Okay, so we can see from distinguish them from the current and time graph, right? Okay, understand that?
Yeah.
And the potential difference and the quantity is increasing, right? It's increasing because the capacitor will get in the electrical energy, will get in the potential difference, okay, and same time they will get in the charge, right? Charge quantity, okay, understand that?
Yeah.
Okay. After we have another charging, okay, and we are going to another discharging energy, okay, like the circuit, the closed loop, the closed circuit, okay, and here's the battery, okay. After battery releasing all the electrical energy to the capacitor, and the capacitor has the full energy, okay, for the electrical energy, has, and we are going to another discharging energy, okay, like the circuit, the closed loop, the closed circuit, okay, and here. Here's the battery. The battery. Okay. After battery releasing all the electrical energy to the capacitor, and the capacitor has the full energy. Okay, for the electrical energy. For the electrical energy. Okay, energy. And if we switch to the point P, okay, I'll switch to the point Q. Okay, and which means collect the point Q. And you can see the right side is like the closed circuit, right? The loop. Understand that?
Yeah.
Okay, the loop. And here's the loop. And the capacitor has become the new battery. Okay, become the new battery. Okay, become new battery. And to provide the electrical energy to the capacitor, that will be dissipated, right? Dissipated by the resistor. Okay, and here, and we can reading the number. Okay, understand that?
Yeah.
So the process we call it discharge the energy. The discharge. Okay, and the process we call discharge. Understand that? Okay, and here the three graphs. The three graphs is related about the discharging process, and we can see the graphs like current, potential difference, and the charge quantity, and all are exponential decay. Why exponential decay? Last lesson I told you. And you asked me the same question. Why the three graphs all exponential decay? The exponential decay curve. Think about it.
Because it's discharging, and then the voltage will decrease, and the charge will decrease because it's discharging.
Okay. Because they are discharging, so the approximately the shape like the exponential decay, okay, the decrease line. And I just want to say when the capacitor discharges through a resistor, okay, through a resistor.
Because it's discharging, and then the voltage will decrease, and the charge will decrease because it's discharging.
Okay, because they are discharging, so the approximately the shape like the exponential decay, okay, the decrease line. And I just want to say when the capacitor discharges through a resistor, okay, through a resistor. When the capacitor discharges through a resistor, like the graph, through the resistor. Okay, here's the resistor, through the resistor. And first, the voltage across the resistor is high. Okay, at the beginning. At first, the voltage across the capacitor, right, is high. It's okay.
Yeah.
Okay. At first, the potential of the capacitor is high. Okay. So then we have so we have a large current flows, right? So we have the large current flows. Okay. And at the moment, as the charge leaves the capacitor, and its voltage decrease, right? Okay. As the charge leaves the capacitor, its voltage decreases, right? Understand that?
Yeah.
Okay. And the lower voltage means a small current, right? So the charge leaves more slowly, and this causes the voltage to drop quickly, right, at the beginning, and then more gradually over the time, right? So we can use the mathematically, the behavior flows or exponential decay function, right? So the graph is like the exponential decreasing curve. Understand that? Right?
I'm confused why for charging the current is also decay.
Why the charging is also decay, the potential or the quantity, right?
The current.
The current is that process, the charging part or discharging part?
The charging.
Discharging.
Charging.
Okay. Like you think about the graph. The battery, the current will cross the battery, okay? And first, look at the graph. Okay, maybe look at the graph. The graph. At the beginning, the current will cross from the battery, okay? And the battery will flow to the capacitor, the charging process. Okay, understand that?
Yeah.
And we know that the energy stored in the battery is limited, right? Is limited, right? At a long time over, and all of the electrical energy will flow to the capacitor. Okay, at the beginning, okay, the current is maximum, right? The current is maximum because the all electrical energy is stored in the battery. So at the beginning, so the current has the maximum, right? Right? Okay, and a long time over, the all electrical energy will flow to the capacitor. So it will cause the battery has the low electrical energy. Okay, so if we have the no electrical energy, the no current, right? So the current that will be the approach to zero. Okay, and in the charging process, the current flows like the exponential decay curve. Okay, because the current flows to the capacitor, the process like the charging process, the electrical energy will flow to the capacitor quickly. The charging process, the time is so quick. So the current will decrease so quickly like the exponential decay, right? Understand that?
Yeah.
Okay. So remember the set graph. The first charging graph is the very particular. The one is the current time graph. Okay, and the other two one, the voltage and the charge quantity, like it's like the charging process the increase, right? Okay, increase to the maximum value. And but the current time graph like the exponential decay. Okay, and in the charging process, all three graphs are decreasing exponential decay. Understand that?
Yeah.
Okay. After that, and look at the summary. Look at summary. Okay, the discharging we can summary that the discharging curves all identical, and the current decreases for the charging process, but increases for the potential difference and the charge sort. Okay, so remember that. Understand that?
Okay, yeah.
Okay, and look at the view knowledge. That is the time constant. Okay, here's the definition for the time constant. The time constant, like the time for the particular second. The particular second is for the in the discharging process. If we discharging the energy to the one moment, the moment is that we have rest of the 37% of the original value. Original value.
Time constant. Okay. Whoa. Whew. So tired. Oh. Ooh. Sheesh. God. Let's play for 10 minutes. Sheesh. This guy's knockback is insane, bro.
than the electrical energy, okay? And the time constant for the charge, current, or potential difference in the discharging.
Time constant of a capacitor discharging through a resistor is a measure of how long it takes for the capacitor to discharge. The definition of time constant for discharging of a capacitor is the time taken for the charge, current, or potential difference of a discharging capacitor to decrease to 37% of its original value. The time taken. Alternatively, for a charging capacitor, the time taken for a charge or potential difference of a charging capacitor to rise to 63% of its maximum value. Okay, so if it's going discharging, then 37% of its original value. If it's charging, then 63% of its maximum value. 37% is 0.37 or 1 over e, where e is an exponential function multiplied by the original value. This is represented by the Greek letter tau and is measured in units of seconds. The time constant provides an easy way to compare the rate of change of similar quantities, example, charge, current, and potential difference. It is defined by the equation tau equals RC, resistance times capacitance.
Process. The capacitor, the energy of capacitor decreases to the 37% of original value, and we call it the time constant. Understand that?
Okay.
Mm-hmm.
Yeah.
Okay. So the time constant is just like the time. It's just like time. The time we define the moment the time taking for the charge or the current or the potential difference, and the discharging process that will decrease the energy will flow to the other resistor. Okay. Just other resistor, and will decrease it to the 37% of original value. Okay, if the original value is the 100, and then now becomes the 37. Okay, becomes 37, and the time interval, the process time interval, the changing time interval, we call it time constant. Understand that? Here's the definition of the time constant. Okay, and alternatively, for the discharging, the capacitor that will decrease to the 37. Okay, 37 of original value. But in the charging capacitor, the time taking, we call it the charge energy to original value of the 63. Okay, understand that? So in the discharging process, the energy of the capacitor decreased to 37% of original value. Okay, and the charging process, the time constant is like the time interval from 37 to 100, right? So the change is the 37, right? And the time taking in charging process, we call it the time taking for charging, right? Understand that? We call it time constant for charging part. Understand that? Okay, and here's the formula for time constant. Okay, the time constant, here's the formula. Okay, and we use the symbol to represent the time constant. Okay, the unit is the second, and is the product of the resistor and the capacitance. The C is the capacitance. Okay, the unit is the farad. Okay, and the R is the resistor. Okay, resistor is what? It's like this. The discharging process, the resistor
Resistance
value.
and internal resistance.
This one, resistor value. Okay, so if we want to calculate the time constant, we just need to find the resistor in the circuit or the capacitance of capacitor. Okay, understand? Okay, and for this, please, the graph. The left side graph to represent the charging process. The charging process, and I just mentioned the energy that will increase by the 53%, right? And the discharging process that will decrease, right? Decrease 2. Okay, and here's the increase 2, right? And we spend the time, we call it time constant. The time interval, understand that? Okay, look for the work example. A capacitor of the 3 nanofarad is a discharge. Okay, in the discharging process, through the resistor of resistance R. Here is the resistance R. The time constant of discharging is this one. Okay, and we want to know the value for the resistor value. Okay, how to do it? How to solve it?
Time constant. Okay. What the hell?
time constant equals the capacitance
Mhm.
times the resistance. So rearrange the equation to R equals the time over the capacitance.
Okay, so you use the time constant over the capacitance of the capacitor, right?
Yeah.
C, right? So we can get in the resistance. Okay, and take into the time constant is the denominator, and the denominator is the 7 nanofarad, and transfer the unit 7 times 10 and negative 7, negative 9, right?
Yeah.
Okay, so we can get in the final route. Okay, this one. And negative 7, negative 9, right?
Yeah.
Okay, so we can get in the final route. Okay, this one.
Remember to check the concept of the exam question. In other words, whether the capacitor is charging or discharging. The definition of time constant depends on it. For a charging capacitor, the time constant refers to the time taken to reach 63% of its maximum potential difference or charge stored. For discharging capacitor, the time constant refers to the time to discharge 37% of its initial potential difference or charge stored. Yeah.
And look at the formula. If you want to go in deeper to understand more the exponential curve, it's like what? And we want to find the formula is about the exponential discharging in the capacitor. Okay, so and we just mentioned that the curve is like
Oh man. Man. Man, this is gonna take forever.
the exponentially decay. Okay, exponential decay. So as the exponential decay, so we can use the mass formula like this one, Okay, to use the mathematical formula to describe the exponential decay equation. Okay, so the first we mentioned the charge quantity. Okay, look at the formula. The formula. The Q, the left Q is which means the remaining charge. Okay, remaining is like the moment we have the remaining charge. Okay, and the Q dirdo is like the initial like the beginning, the value, right? And this is the Q dirdo, and this is Q remaining, right? Okay, understand that?
Yeah.
Okay, and here, and I want to find the ending point in the time constant interval. Okay, maybe we can find this P1. This one P2, this one P3, and we want to find corresponding the point 3 and getting a charge quantity is what? Okay, is what? So we can use the formula, the exponential decay equation. Okay, and we need to understand this one. This one is like the Q double times E and the negative T over the R constant times C, right? The denominator RC is what? Time constant, right?
Oh
The
yeah,
RC,
yeah.
Yeah, it's time constant. Okay, and the denominator the T represent the elapsed time. Okay, which means that we have the dissipated time. Okay, if we spend
Live for 8 hours. When the capacitor discharges through a resistor, the charge stored on it decreases exponentially. The charge stored on it decreases exponentially. The amount of charge remaining on the capacitor Q after some elapsed time T is governed by the exponential decay equation. Okay. Amount of charge Q equals initial charge stored Q0 times exponential function to the power of negative time elapsed over circuit resistance time capacitance, which is the time constant.
The 2 second, okay, and we can get in. Take the 2 second. If t is 2 second, okay, and we can take into, and we can get in. After we discharge the 2 second energy, and the rest of the charge is what? Okay, use the formula. Understand that?
Oh, yeah.
Okay, so here's the formula 1. Okay, it's related to the charge quantity, right? Okay, and the other formula is about the potential difference. Okay, or current. Like, and we can call the Ohm's law. Okay, the Ohm's law tells us the potential equal the product of the resistance and the current. Okay, and so if we have the same graph of the potential difference over time, so we can get in the approximately the same graph of the current over time. Okay, so the time and the current obey the same equation of the exponential decay. Okay, so the formula unchanged, but change this one and this one. This one is the at the moment the sum time, the after sum time current. Okay, like the remaining current. Okay, and the either is the initial current. And look at the graph.
But this is for discharging only. The exponential decay equation for potential difference can be used to derive a decay equation for current. It follows that initial potential difference where, okay, therefore substituting IR for V gives this, canceling R from both sides to give the exponential decay equation for current.
The current over time graph like this, exponential decay, okay? And we also use the formula to find the rest of the current, okay? If we spend then if we discharge 2 seconds and corresponding the remaining current, okay? If we discharge the 3 second and getting the remaining current I1, okay? Understand that?
Okay.
I2, I3, understand that? So the charge quantity and the current charge quantity obeys the same exponential decay equation. And I just want to know the potential is also obey the equation, right? Or not? Potential is also obey the exponential equation. This one, exponential equation or not?
Yes.
Okay, yes, no problem. Okay, look at the work example. If the turn capacitance of the mile capacitor fully charged, then we have fully charged, right?
Yeah.
By the travel power supply, and then we will discharge the resistor. The resistor resistance is 1,000 only, and we want to know what is the discharge current after 15 seconds. Okay, how to solve it? Use which one formula? Use which one formula? Use which one formula? And we want to know the discharge current. So we
Fully charged by a 12-volt power supply and discharged through a 1K ohm resistor. What is this discharge current after 15 seconds? A 10 MF capacitor. What is the discharge current? V equals IR. 15 seconds. (15/10). How has it increased? Oh my god. Initial current. I should be correct.
Might mention the current formula, right? Use which one formula?
Use the
One, right? About
current, yeah.
okay. So and we want to after the 70 second the remaining charge, right? The remaining current. Okay. So we can use the formula I equal initial zero. Okay, and E and negative T over RC, right? Okay. So we know some variable. We have no some variable. Which variable that we have no? Which variable? The resistor
Resistance,
and capacitance and
the time.
the time. Okay. And how to use the potential? How to use the potential of the current in the equation?
V equals IR.
Okay. So we maybe use the Ohm law, right?
Yeah.
The potential equal the current times the resistance. Okay. So if we can use exponential equation, decay equation to find what? To find at the moment the remaining voltage, right? The remaining voltage, right? Remaining voltage. So we can use the remaining voltage to find the current. Okay. Use the voltage, the potential over resistance, the 1 halving and times the C, right? The C is the turn and times what? The mile transfer unit.
10 to negative 3.
Okay, 10 negative 3. Okay. And we can use the other, might be the potential, right? We want to find the remaining potential, so we might use this one, okay? The initial potential is the 12, okay, right? So they take the variable into equation, so we find the remaining potential, right? Remaining potential. Okay. And after we have found the remaining potential, so we take this. Okay, we take it. So we might think about the phone one, okay? But we don't know initial, right? We don't know the variable initial current, right? Okay, we can find the initial current, right? Okay, right? And or maybe we can use the Ohm's law to find the initial current. Remember, the first formula.
2.7. I got it wrong. Negative 1.5. 0.012 times e to the power negative 1.5. Yes, that's what I typed. Oh my god, I typed 10. It's okay. Remember, you can work out initial quantities like current or potential difference or charge using the equations. Yep. I know that. Well, you then usually have enough information to substitute all necessary values into the decay equations. I'm sure going to remember that.
The Ohm's law, the second formula, the charge process, right? Okay, the charge process, right? And look at it, this one. This one is what? This one, they will change the exponential decay into the log. And look at it, this one. This one is what? This one, they will change the exponential decay into the log.
Okay. Using Q. Got it.
Your log equation, right? You have now the mass, right? So we can use the formula to change the equation. So how to change the exponential equation into a log reciprocal? How to change this one into the log reciprocal?
Bring the Q0 to the left.
Log in E and negative T over the RC, right? So we can get this one. So we're getting this one, right? Okay. So the log equation that will become the negative time over the RC, right? Understand that?
Yeah, okay.
Okay, and the left side is the logging the initial quantity and the remaining quantity, the fraction, right? Okay, and we can transfer into the minus equation. Okay, transfer the fraction into the difference, right? Okay, so use the remaining logging charge quantity and minus the initial quantity, right? Logging, right? So we can get this one, okay? Understand that?
Yeah, okay.
And we shift the initial value, the constant, to the right side, and we can get this one. Okay, why are we getting this one? Because we want to find the straight line graph, okay? The straight line graph. And this one represents the y-axis, okay? And this one, the time t, represents the x-axis. Okay, so then the form will become the what? Become what? Become what? Become linear equation. Become linear equation, okay?
Oh,
The y equal mx plus c, right?
Yeah.
The form, right? This form, okay? And so we can get the m is equal to what in this equation?
Negative 1 over C.
What is m? The gradient.
negative 1 over RC.
Okay, the gradient is negative 1 over RC, right? Okay, what is the intersection with the y-axis? The c.
ln Q0.
Okay,
Yep.
log q and the okay. So then we can use the graph to find the gradient, right? To find the intersection with y-axis, okay? Understand that?
Yeah.
Okay, so this formula is that we transfer the exponential decay equation into the log equation. Why we use the log equation? Because we want to find the straight line graph, okay? And using a best field line or the straight line graph to find the RC, right? To find the initial value, okay? So the graph like this, right? Understand? Understand that, right? Okay, so the gradient represents the negative 1 over the RC, okay? And the intercept with the y-axis value is the initial value, the log initial value of the charge quantity, right? Understand that? Okay, so remember the formula, right? And the straight line, the gradient is negative, right? Okay, because here's the negative, right? Understand that? So
Yeah.
if I want to find the RC, the time constant, how to use the graph to do it? How to use the graph to do it, to solve it?
Find the gradient.
Find the gradient, do it. Yes, I want to use the gradient. I want to use the graph. The first, I want to use the graph to find the time constant. The first thing you mentioned that we can get the gradient, okay? And how to use gradient to get what? To get the time constant. How to use the gradient to find the time constant? The gradient is m, right? So m is negative RC. Okay, if you want to find the time constant, so RC is what? It's 1, negative 1 over m, right?
Yeah.
Okay, so we can transfer like this, right? Understand that?
Yeah, okay.
Okay, understand. Okay, and look at it, for example, when the capacitor charges, the voltage across it varies with the time t. Okay, and the graph showing the variation. Okay, the y-axis is the fraction, not
Capacitor discharges the voltage V across it varies with time t. A graph showing the variation of ln V against t is shown for a particular discharging capacitor. A capacitor discharges the voltage across it varies with time t. This is the graph of ln V over t. Use the graph to determine the initial voltage across the capacitor. Initial voltage across the capacitor is 2.1.
With the time t. Okay, and the graph showing the variation. Okay, the y-axis is the fraction, not the graph is the charge quantity. Okay, and the x-axis is the time. Okay, and use the topic just want us to use the graph to determine the initial voltage across the capacitor. Okay, how to solve it? How to solve it? How to solve it? The y-axis has changed the log in V. The V is the potential difference. Okay. So the equation above the graph, here's the equation. Which equation that we might use?
The first one.
Okay, the first one. That we might use the first one. And the first one is log in V equal the negative 1 over RC, right? And times T and plus the log in delta. Okay, log delta V. Okay, so how to use the graph? How to use the graph to find the initial voltage? Not time constant. Initial voltage. How to use the initial voltage?
Find the intercept.
Okay, the intercept value is 2.1, right?
Yeah.
The C represent the log in, right? Okay, so and we can use the calculator to transfer it, or might use the initial value is the E, right? And 2.1, understand that?
Yeah.
Okay, that is rule of the log in rules to transfer into the exponential, okay? And the log function transfer into the exponential. Okay, like this. Understand that? The topic. Is there any problem?
No problem.
Okay, so the discharging process that we have transferred the exponential decay into log equation. Okay, a log equation can be written as the linear stream, right? The straight line. Okay, the straight line that we have the gradient and intercept with y-axis. Okay, so here is the three equation. Okay, the first one and another one is the log in q, right? Equal the negative 1 over RC and times t, right? And plus the log in q and delta. Okay, from the three equations. Okay, is there any similar that we will find? Is there any similar of the three straight line? Is there any similarity?
All are decreasing gradient.
Okay, the first all decreasing. And how about gradient? The gradient. How about the gradient? Compare their gradient. Is it equal or not equal? The gradient.
Equal.
All equal.
Yes, all of them are equal. Okay, equal gradient. Gradient value, right? Okay, but which variable is not equal? Which variable is not equal from the graph?
The intercept.
Yeah, different intercept with y-axis. Different intercept with y-axis. Okay, understand that?
Yeah.
Right? Okay. And finally, here is the graph that tells us, okay, to mention.
You need to know how to derive decay equations for PD and for current from the decay equation for charge, as well as how to use and interpret natural logarithm equations. If you can understand that these natural log equations are linear because they are plotted as a graph in the form of y equals mx plus c, then you are well set for the exam questions on this topic. Remember, the gradient of the straight line is given by 1 over RC, negative 1 over RC. The y-intercept of the line represents ln q or ln v or ln I. Derive decay equations for PD and for current from the decay equation for charge. Derive it from charge? Oh, wait. Okay, not the natural log ones. Yeah, I know how to do that. From charge, you find it VC Q over V equals C. So Q equals VC. V equals Q over C. V equals Q over C. V equals I R. R I. So V equals IR. And the R cancels out. So yeah.
The first, the gradient of the straight line is given by the -1 over the time constant, right? And the second, their y-intercept with the line represent the initial login charge quantity or initial potential difference, right? Login, right? And login initial current, right? Understand that?
Right.
Okay. So this is the chapter, okay? It's the two chapters that we have done, right? And the content, look at the content. Okay, the content, okay? The content is about capacitance. Okay, quick review. The first, in this chapter of the capacitance, we know the capacitance is what? Is the measure how large or how small of the capacitor, right? To store electrical energy, okay? And the second, and we learned the equation for energy stored by capacitor is what? The equation using charge quantity and the capacitor to calculate the energy stored.
Stores electrical energy.
In a capacitor is what? The equation. The energy stored by
Energy stored by a capacitor. I fucking forget. Energy stored by a capacitor. W equals 1/2. QC? I don't know.
by the capacitor equation is what? You remember?
Forgot.
Okay. The first, the capacity is the charge quantity, right? Over potential, right?
Oh.
Okay.
Capacitance is charge over voltage. Yep, I remember that.
And the energy is the area of the charge quantity over the potential, right? So that is the 1/2 times the Q M D, right? Understand that?
QC, right?
Okay. And finally, the formula will change, right? Understand that? Oh no. Sorry, I'm mistaken. It's not the 1/2 times the Q times the V. It's what?
QC.
It's C V, right?
CV? I don't know anymore, man. C times V is charge, though. Man. Fucking know this shit no more, man. Man, I don't know, man. I don't know, man.
Okay. The equation. And the next one is the curve, right? The curve that can be divided into two sections. The first section is the charge curve, okay? The particular one of the charge curve is the current over the time graph, right? Okay, that is the decreasing, right? And the other two one is the increasing, right? In the charge curve, okay? And the discharge curve, the three graphs, the current, the potential, the quantity, all exponential decay, right? Okay. And next one is the exponentially discharge in the capacitor. Understand that? And we derive the equation. Transfer the exponential decay equation into the linear straight line, right? Okay, understand that? Is there any problem? Okay, the final one, look at the core practical. That is the equipment. The purpose of the equipment is to investigate the capacitor charge or the discharge. Okay. Okay, look at this one. This one, we are going to investigate the capacitor charge or discharge. So the first.
The overall aim of this experiment is to calculate the capacitance of a capacitor. This is just one example of how this required practical might be carried out. Independent variable time, dependent variable potential difference, control variables, resistance of the resistor, current in the circuit. Independent, the one that we control, the one that we set is time. Dependent variable, the one that we measure, is potential difference. Equipment, switch, capacitor, resistor, battery pack.
First, we have to learn the
voltmeter,
M of the experiment.
stopwatch.
The first one, the M is to calculate the capacity, okay? Which means we have to calculate the C, right? The Fred, okay? And here's one example of how to
C equals charge over V.
construct the fractal, okay? The first, we have to find the variable, okay? If we do the equation, the first step, we have to find the variable, okay? Right? Right?
Yeah.
Okay. The first, the variable includes the time, okay? The second one, the dependent variable, is the potential difference, okay? And here's the control variable. Control variable is really about the resistance of the resistor and the current in the circuit, okay? Here's the equipment list. The first, the apparatus that we need is the switch, and the purpose is what? To switch between the charging and the discharging circuit, okay? And the second one is capacitor. The capacitor, that means the purpose of the experiment is to calculate the capacity of the capacitor. So we have to, this one, right? Have this one, okay? And another one is the resistor. The resistor that we choose, the larger one, the 10,000, right? And the purpose is to charge the capacitor, okay? Understand the apparatus and the purpose, meaning, understand? Okay. And the next one is the battery pack. And here that we need the voltmeter and the stopwatch. The purpose of stopwatch is to measure the time taking for the capacitor, okay? That convenient for us to calculate the time constant. Okay, calculate the time constant. Okay, and here's the resolution. Okay, the resolution told us to reduce the error, okay? And here's the method. Okay, the graph like this. Okay, so I just want to know if we switch to the X, and there will become what? Switch to X, there will become what?
Charging.
Yeah, there will be the charging, okay? There will be the charging process. Okay, if we switch to the Y, okay, there will be what?
Discharge.
Discharge, okay, understand. Okay, discharge. And so the different switch, right? Different switch to the different point that we have the different process. The previous, this one is the discharging, is the charging process, okay? The current flows to the capacitor, okay? Is to discharge the capacitor, okay? And after the energy dissipated by the capacitor, okay, then we switch to point Y, and the process will become a discharging process, okay? And then we need the voltmeter to measure the initial potential, okay? Right?
Yeah.
And we use the voltmeter to measure the initial potential of the capacitor, so we can put the initial in the discharging process. The curve like this, right? The V, the T, so it's the initial. So it's the initial value. Okay, initial value, and use the initial value. Okay, and here's the resistor to dissipate the energy from the capacitor. Okay, understand that? And the next step to set up the data, right? Use the stopwatch to record the time. Okay, use the voltmeter to measure the initial or different potential difference, right?
Yeah.
The different time corresponds to the different potential difference, right? Okay. So finally, then we can use this equation to analyze the results, right? Okay. And here's the decay equation, right? Exponential decay equation, right?
Yeah.
Okay. And the transfer, if we transfer into the linear straight line, okay. And here's the log V equal the negative T over RC, right? And plus, right? The log initial, right? Understand that?
Yeah.
Okay. This formula helps us to analyze the result. And after that, then we can plot the graph, like the linear form, the graph like this. Okay. The y-axis is potential, the axis is the time, okay? And the line will be what? The exponential curve that will transfer into the linear. The y-axis is log V, the axis is t, right? And here is the linear line.
Yeah.
Understand? The y-axis is the initial value. Okay, the gradient equal -1 over RC, right? Understand that? Right?
Yeah.
Okay, no problem.
No problem.
Okay, so this is the one of the example that we use the potential difference and use the time, use the charging process or discharging process to analyze the results and transfer the exponential decay equation
Become linear equation.
into the straight form, right? And then we use the straight form to easily get the initial value, okay? To easily get the gradient, okay? And finally, if we want to find the time constant, okay? Then we find the time constant. The equal is -1 over gradient, right? Okay, and time constant is the product, the capacity C, and times resistor, right? And transfer. The equipment purpose is ask us to find the capacity, right? So that we use the -1 and the gradient, and times the resistance, find the value, right? Understand that? So this is the result that finally we get. The capacity,
Okay.
right?
Yeah.
The capacity of the capacitor. Okay, understand that?
Understand.
Okay, so the chapter relate about the capacity and capacitor and the charging process, the difficult part, the most difficult part that we have now, okay? And here is the homework, okay?
Okay.
And I will send you and you down, right? If you're down and you send me, okay? Understand that?
Yeah.
Okay, another question. The next time that you are available for studying is
Money is not pouring in. $13? Oh, so is the views popping off here? $13.27. 13.39. Jesus, where is this income coming from? No one's in chat. I'm going insane. Oh, I'm going insane. That's a pretty good explanation. It's a pretty good explanation. This is some crazy stats. Crazy, crazy.
I forgot it. I will open the broadcast. Okay, I see.
Yeah.
You see. So I plot the graph of the two plate, okay, and I refer to the d is the distance in the work example. The distance d, the d represents the distance between the two plates, not the distance between the two particles, okay, not a particle to another particle, okay,
Yeah. Okay.
not a d, okay, and I call it d.
Electric field is set up between two pairs of oppositely charged plates.
D1. This is a D2.
Which set creates the largest electric field strength? Oh my god. Oh my god. Set X and set Y. They're a set. They're a pair. Oh my god. Oh my god. Wow. Eva, I've been here for 8 hours by now. Almost 9. Please save me from this. It's been... Man, I said I would study until I finally collapse, but I haven't collapsed yet, so I have to continue studying. I've been streaming for 8 hours. I'm gonna die. But that's a good thing. If I collapse, I get to end stream. Keep studying? I'm gonna die. Oh man. Set X and set Y. Oh my god. Oh my god. It finally makes sense now. Don't die. But well, I will collapse. I will collapse. That's when I stop the stream. I've been studying for 8 hours. Not straight, but not 8 hours straight, but I started studying 8 hours ago and I'm still going. Best case scenario, yes.
Okay, and we are not in the two parallel plates that we have the same E, right? The uniform electric field. The uniform electric field. So which means that the E constant, right? I told you, right? The E is constant. Understand?
Yeah.
Okay, and here's the two parallel plates. Here are two parallel plates, and we have the equation there. The E equal the potential difference between the two parallel plates. Okay, the potential represents the potential difference between the two parallel plates. Okay, and the D is the distance between the two parallel plates. Okay, so you can see transfer. The E is a product of the potential difference. Is the product of the E times the D. Okay, understand this?
Yeah.
And
I want to ask what the V is representing.
The V is a potential difference between the two plates. Potential.
Then why is it different for the two plates? Like for X and Y, why is it different?
Why is it different in a charge particle?
For the X and Y, why is it different at the 2 points in the question?
Because their electric field strength is different.
You mean the V1, here's the V2, right?
No, in the question it says there's set X and set Y, and then they have different gradient. That means they have different V.
Yeah, the different gradient has a different V.
But they're in the same. They form the same like two. The two plates are forming one field. And how come there's two different V?
Okay, because in the two parallel plates, and
because they're not one set, they're different sets. I can't believe I made this misunderstanding that has ruined my entire life.
the external, that we have the current, okay, the battery, okay, and the current flows. You can see the graph. The current in the closed circuit, the current flows to the positive plate, right?
Yeah.
And positive plate, and in the field, the positive the positive plate that produce the electric field from the positive, right, from the positive plate to the negative
I
plate,
have
right?
3 people
Yeah.
watching me
With
right
few
now.
lines like this, right? And every single line just parallel,
Guys,
right? Every single
teach
line
me
just parallel,
physics.
okay? Understand that?
Yeah, understand.
Okay, and you understand that if the E is constant, right?
Yeah.
The electric field constant, and here's the D, and here's the D. Here's the potential. Here the V, the potential means the two plate, the difference, right? Like here's the D, like here's the V1, this is V2. The D, the V is the absolute value of V1 minus V2.
A while ago, I'm low-key being schizo. I was like, why is Chris answering the video and the video is answering Chris? Wait. Cause I was having class, right? I was having class with my tutor, and I was using this to record it. Now I'm going back to watch it. Were you watching me while I was with my tutor? So you thought the tutor was a video, and the video was actually responding to me. You thought that, right? You thought the video was responding to me, but it was my actual tutor, because it wasn't a video. It was the live tutoring session, right? Yes, you get it now. You thought it was a video, but it was the actual tutor talking to me.
Here's the V1, this is V2.
Oh,
The D,
okay, that's
the
funny.
V, the V is the absolute value of V1 minus V2. Understand that?
Yeah.
Okay.
What? V is V1 minus V2? Oh, yes, it is.
Okay. So I mean the V. So here's the equation. The V is the product of the E times D, and you see this right. The V1 that will with the D increase, right? The D increase with the D increase, and the potential V, right? The endpoint, the endpoint in the field lines, okay, that will decrease, right? That's correct. Understand that? Mm-hmm.
Oh, yeah. Oh. So there's a potential difference.
Okay. Yes. And you refer to the V is the potential in every point in the field lines, and you said it is right. The V.
Oh, great, the Wordle is up. Let's play it. Wow. I don't know what the fuck this word is, bro. I don't know what the fuck this word is. Can someone help? There's 2 people watching me. This is not gonna work. Has Leonard gotten it? Leonard has not gotten it. I'm gonna sleep at 1. That's gonna be... it's gonna be my limit today. Clone. Alright. Why? I cannot have any success.
Is the in every point with the D increase, the potential, the point potential, they will decrease. And I mean the V, here's the V, is the potential between the 2 plate, right? Between the 2 plate. The V is the difference, right? The V is the difference. Here's the difference. Okay? Understand that?
Okay.
Okay, so here's the equation. So the E is constant, and with the D increase, the absolute value of the differences of 2 points, right? The potential difference it increase, right?
So on the graph is the V the potential difference or the V on each plate?
Yeah.
Is it on the plate or is it the difference between the 2 plate?
Difference.
It's a different to the 2 plate.
You got it in 5 tries.
And then why is there 2 different V's? On the
Man,
graph.
if I had one more
Like the
try, I
Pranav
would have
graph,
won.
right?
I would have gotten it.
Electric field graph.
If I had
or
7
another
tries.
one.
Oh my god, I almost got it, bro.
This one.
In the question.
Okay.
The worked example.
The work example is referred to the 2 parallel plates. Okay, 2 parallel plates. And in the work example, the V in the work example represent the potential difference between the 2 plates, right? I suppose the left V is V1. Okay, left side of the plate, the point potential is V1. Okay, and another side of the plate is the V2. Okay, right?
Yeah, I wrote enjoy. Did you do it too? Or like you just directly got envoy? There's 3 watching.
And in the topic in the work example, the V represents the difference between the V1 minus V2. Okay. And we know, you said just right, with the D increase. Okay. With D increase, the point potential decreases, right?
The potential
right.
decreases, but uniform potential increase. Okay.
Understand that? So V1 and will greater than the V2. Okay.
Yeah.
Suppose the point potential, the initial value is 100, and with the D increases, the initial if the D1, here's the 2, suppose it's the 20, and if now I increase the distance between the 2 plates, okay, with the D increase and the potential point potential decreases, so the V2 will become the 8. Okay, so the change in the potential, right? Now the change in the potential, the V potential, V, they will become bigger, right?
Yeah.
Okay, it's just because the 100, the original value is the 100 minus the 20, but now that has changed the 100 and the minus the 8, right? So in the work example, the V represents this, the change in the potential. Okay, so that's the reason why the D increase and the potential difference between the 2 plates increase, right?
Yeah.
Understand that?
Yeah, I understand that now.
Okay, and talk about another is the point potential. Okay, the point potential. The point potential refers to the ending point, like if the electric field, the field lines, and I draw from the center to the infinity, right? And suppose here's the point 1, here's the point 2, and the point 3. Okay,
Jesus
with the increases,
Christ,
with the distance increases, right? Okay, the distance between another charged particle. Okay, and I suppose the distance is d, okay, right?
Yeah.
And with the d increases and the potential v1, the point potential, suppose the point 1, the potential corresponding the potential 1. Here's the point potential is potential 2, okay? Here's the potential 3, okay? With the d and d increases and the potential point potential that will decrease, right? So the v1 greater than v2 greater than v3, okay? Understand that?
Yes. Yeah. Yeah.
Okay. If I see the potential difference in v1 to the v2, okay, and v1 to the v3, which one is bigger?
V1 to V3.
Yes, no problem. Okay, so the v1 minus the v3 is the v, the work example referred to. Understand that? Now,
Why did he draw an arrow?
Wait, no, not really.
which one you confused? You feel confused?
Why does it connect to the V equals ED?
V equals ED, right? So you're confused about this equation, right? This equation.
No, why are we doing V1 minus V2 and V1 minus V3?
Okay. I just used the minus to represent the potential difference, okay? Potential difference refer to the two-point potential difference, okay? The potential difference, okay, is the difference of the two different point potential, okay? So V1 minus V2 means the potential between V1 and V2. So I use the potential at point 1 to minus the potential at point 2. Understand that?
Yeah.
Okay, right? And V1, I talk about V1 is the potential at the reference point, okay? The V2 and V3 are potentials at the R point and further from the negative plate. Okay. Now understand that?
Yeah.
Okay. So in the work example, here's the keywords. The keywords. If the next time you meet a new work example, if we meet the electric field, okay, the uniform electric field, then we use the formula, this one.
I didn't get that.
V2 and V3 are potentials at the R point and further from the negative plate. Okay. Now understand that? And the potential at point 2. Understand that?
Yeah.
Okay. Right? And V1, I talk about V1 is the potential at the reference point, okay? The V2 and V3 are potentials at the R point and further from the negative plate. Okay. Now understand that?
Yeah.
Okay.
I don't.
Right? Yeah. Okay. And the potential means this one
The
and this one.
physics thing
This is V1, this
is
is V2,
hurting
okay?
your brain.
The difference between the two
Have fun.
potential point potential,
Bye.
okay? And V.
Bye bye. Yeah, you gotta be glad you're not doing physics, cause I'm whatever, man. See ya.
Equal the E times D. Understand that? And D increases, so the V is a 2-point potential, right? D increases, so the V increases, right? Understand now?
Are we moving the the charge plates? Are we moving the plates to be further away?
Between two parallel plates, the distance increase, right?
Yeah. How?
If I make the D increase, and you talk about if I take the right side or I use the left side to go in further, okay, or separate more further distance, okay, and that will make the distance become bigger, right?
Yeah.
Okay. And here's now the potential between the two plates that will increase, right? Okay. So you can see the graph, okay. And so for example, the graph with the axis is the D, the Y axis is the potential. So here is the line, right? Understand that?
Yeah. Yeah.
Okay. No problem. Now.
Yeah. No problem.
Okay. Look at the question, the homework, the first. Okay. The question 1. And you can see the switch is closed. Okay, the switch is closed. So here become the charging process or discharging process.
I don't fucking know. What kind of fucking circuit is that? Is it charging or discharging? You could be both, bro.
Charging.
Charging. This one, correct. And the current will go through this one, right? The current will flow through the port we play, right? So the process is called.
Leonard, please help me. You're my only hope. Yes, the landlord. Is he gonna help me? Landlord is here, right? He's gonna help me? Leonard! Check the others. So this is 6 days ago. So this is the first ever class I've had. Electric fields. Let's check all the way
Yeah,
from
charge
the
particle.
start.
Okay. One. And charge quantity 2, the product of the charge quantity, and the over the r square, which means if the left one we have the positive charge. Okay, so we're doing it. The first one is the definition. We have to memorize the electric field
Region
definition.
of space where
And the field
charged
will
particles
to in the particular.
experiences a
This one,
force.
our highlighter. So the
Yes,
definition
I
of
got it
electric field
right.
is defined as a region of the space in which where a charged particle experiences a force, right? So we always call it the force field. Okay. Right?
Yeah.
Understand this? Okay. And this one. We are going to calculate the how strong or how weak that is the electric field. So
Electric field. Electric field strength. Okay. Electric field strength. Oh, big help, big help. Oh my god.
And the denominator.
$125 XP. Oh.
is the positive graph. So V over D, right?
Calculate the electric force acting on a stationary charged particle between the plates that has a charge of 2 points. Two parallel metals are separated by 3.5, potential difference of 7.9 K. So we have the electric field strength and then calculate the force. Force over charge. Force over charge. Stationary charged particle between the plates. Charge times electric field strength. Okay.
Right?
Yeah, calculate E first.
Okay. And second, use another formula. Times charge quantity, right? Okay, this is the electric force. In the beginning, we have learned.
E times charge quantity. Yeah, I think so.
This one. That was 2, 4. Okay, this one, right? Electric field force, right? This one, F, right? Okay, so F equal the product of the E times Q, right? And we use the first formula to copy the E, right? And we need to find the charge quantity, right? So we can get the answer is the force, right? Okay. Understand it right now?
Yeah.
Okay. Substitute. Use
V
the
over D.
D over D and times Q, right? The Q is the 2.6 and then times 10 and negative 5, right? And negative 15, right? Okay. And to take every variable into the equation. And the voltage is the 7.9 and electric field strength, right? And electric force between the two charges. And 7.4 temperature is the electric field due to the point charge and electric field and the potential, right? Okay. And we have learned the electric field between the parallel plates. Okay. And the 7.7 is the electrical potential. Okay. So this is the what we have learned in this lesson, right? Okay. So today's lesson is over.
I'm done with this video. I'm done with it. Ah. So tiring, man. Let's revise. So many new equations to memorize. I don't think I can memorize them in one day. 4 equations for electric field strength. Crazy, man, crazy. This is abuse.
The infinity is in the right.
Yeah.
Okay.
Okay, and then we go through some questions. And then after the questions, we go through capacitance. Okay. I'll jot down the equations for the capacitance. Finish the questions that he did for me. And then here is even more on capacitance. God, I'll do it tomorrow morning. I don't need this. Save this. Top fans. Alright, it's late enough. I think I'm gonna go to sleep. My to-do list will be to go through these questions and then note down the equations here and here. And then I have a lesson around here. I have a lesson here. 1 hour looks so short. It looks so short on this timeline. 6 hours and then 5 hours. Alright. Alright then, I'm gonna go now. Is there anything else I want to say? Oh yeah, tomorrow I'm gonna be streaming for 12 plus hours. I'm gonna go to the gym or an afternoon lunch. I'm gonna go to lunch tomorrow midstream and also the gym midstream. So it's gonna be 12 plus hours, but like I'm gonna be missing for like 2 to 3 hours in tomorrow's stream. But yeah, I'm gonna be studying the entire day tomorrow. And hopefully finally finish this chapter of physics, bro. This is so like such a waste of time, man. I gotta go back to chemistry and math. Jesus, I also have chemistry to go back to tomorrow. And then I have to start math sometime soon. Oh my, I don't have enough time in the day, bro. Alright. That's gonna be it.